Have you ever looked up at the night sky and wondered, truly wondered, how it all began? Not just our world or our sun or even our galaxy, but everything. The vast velvet darkness dotted with stars feels eternal, but the universe was not always here. It had a birthday, it had a first breath, and those earliest moments of existence hold secrets so profound they challenge our very understanding of reality itself. What happened in the first fraction of a second after the Big Bang? How did something come from nothing? And how did that fiery, chaotic infancy give rise to the breathtaking cosmic structures we see today? We are about to embark on a journey unlike any other, a voyage back in time to the very dawn of everything. We'll be exploring 30 of the most compelling, puzzling, and utterly fascinating mysteries from the universe's earliest chapters. From the mysterious forces that shaped space and time in those first fleeting instants, to the formation of the very first stars whose light still whispers to us across billions of years. This is not just a story about science, it's a cosmic detective story, one where each clue pulls us deeper into the grandest narrative of all, our own origins. You are part of this story. Every atom in your body was forged in the heart of an ancient star, and every breath you take is woven into this epic history. So come with me, let's explore the questions that have captivated astronomers, physicists, and dreamers for generations. Questions about dark matter, primordial energy, and the birth of galaxies, questions that don't just define our past but could illuminate our future. By the end of our journey, you won't just see the night sky the same way again. You'll feel it. Our journey begins at the very precipice of time itself, with the greatest and most fundamental mystery of all, the singularity. What happened before the Big Bang? What could possibly exist before time? This question is the foundation upon which all of cosmology rests, and it's a place where our logic, our intuition, and even our established laws of physics completely break down. We often picture the Big Bang as a massive explosion in an empty void, but that's not quite right. It wasn't an explosion in space, it was the explosive appearance of space itself, and time along with it. The universe began not as a point in space, but as space itself, unimaginably hot and dense, smaller than a single atom. This starting condition is what scientists call a gravitational singularity, a point of infinite density where the mathematics of Einstein's theory of general relativity simply stop working. The equations produce infinities, which in physics is a clear signal that the theory is incomplete. It's like having a map that shows a road leading straight off the edge of the page into a blank unknown. So, if our best theory of gravity can't describe the beginning, what can? This is where the realm of theoretical physics opens up, offering a spectrum of breathtaking possibilities. One compelling idea is that our universe was born from a quantum fluctuation in a deeper, pre-existing reality. A tiny bubble of energy that, through a process called quantum tunneling, suddenly and rapidly inflated into the cosmos we know. Think of it like a bubble spontaneously forming in a boiling pot of water, but on a cosmic scale. In this view, what we call nothing might not be truly empty at all, but a seething, frothing sea of potential, a quantum foam from which universes can blink into existence. Other theories take this idea even further, suggesting our universe might be just one bubble in a vast, eternal cosmic foam, a multiverse. In this staggering concept, the Big Bang wasn't a unique, one-time event, but a common occurrence within a much grander, perhaps infinite, meta-universe. Each bubble universe could have its own unique set of physical laws and constants. Some might collapse instantly, while others, like ours, are stable enough to allow for galaxies, stars, planets, and life to form. It suggests our entire cosmic history is just one page in an infinite book. There are even more radical proposals, like the conformal cyclic cosmology, which posits that the universe undergoes an endless cycle of expansion and renewal. In this model, the distant heat-death fate of our universe spread out into a vast, cold emptiness somehow becomes mathematically identical to the high-temperature, high-density singularity of a new Big Bang. The end of one cosmos becomes the beginning of the next in an eternal, timeless loop. It's a concept that challenges our linear perception of time in the most profound way. So, while we may never have a definitive answer to what came before, the very act of asking the question pushes the boundaries of human knowledge to its absolute limit. It forces us to invent new mathematics and new physics, to question the very nature of reality, time, and existence. The mystery of the singularity is not a dead end, it is the ultimate invitation to explore. But if the singularity is the edge of our map, then cosmic inflation is the first, breathtaking path we've managed to chart beyond it. This theory tackles one of the most puzzling observations about our universe, its staggering uniformity. No matter which direction we point our most powerful telescopes, the cosmos looks almost exactly the same. The temperature of the faint afterglow of the Big Bang, known as the cosmic microwave background, is identical to within 1 part in 100,000, whether we look left, right, up, or down. For this to be true, every part of the universe must have been in contact with every other part, able to exchange heat and reach a common temperature. But in the standard Big Bang model, that's simply impossible. There hasn't been enough time for light or heat to travel from one distant horizon to the other. It's a cosmic mystery often called the horizon problem. In the late 1970s, a young physicist named Alan Guth proposed a radical and elegant solution: cosmic inflation. He suggested that in the very first fraction of a second specifically, from 10 to the power of -36 seconds to 10 to the power of -32 seconds after the Big Bang, the universe underwent a period of hyper-exponential expansion. It didn't just grow, it exploded in size, inflating by a factor of at least 10 to the power of 26. To put that incomprehensible number into perspective, it's like blowing up a subatomic particle to the size of a galaxy, and then doing it again, in a span of time so short it makes a nanosecond look like an eternity. This incredible burst of growth solves the horizon problem effortlessly. It tells us that the entire observable universe was, in fact, once a tiny, microscopic patch that was in perfect thermal contact. Inflation then stretched that tiny, uniform patch to become larger than our entire visible cosmos, preserving that smoothness across vast distances, but that's not all it explains. Inflation also answers the flatness problem, the observation that the geometry of our universe is almost perfectly flat, not curved positively or negatively. Inflation would have stretched the fabric of space-time so dramatically that any initial curvature would have been smoothed out, just like inflating a balloon makes any small section of its surface appear flatter and flatter. Perhaps most wonderfully, inflation provides the origin story for everything we see. The theory predicts that quantum fluctuations, tiny, random variations in energy that occur even in a vacuum, would have been magnified to astronomical scales during this rapid expansion. These minute ripples in the fabric of spacetime became the gravitational seeds for all future structure. Every galaxy, every star, every planet we see today, and indeed the very large-scale cosmic web, is a direct result of those quantum fingerprints stretched across the sky by inflation. We are essentially seeing quantum mechanics written across the largest possible canvas. Yet for all its predictive power and elegance, cosmic inflation raises profound questions of its own. What was the engine that drove this incredible expansion? Physicists call it the inflaton field, a hypothetical field of energy that permeated the early universe and possessed a unique property: a high-energy state that caused gravitational repulsion, pushing space apart instead of pulling it together. But we have no direct evidence for what this field is or how it fits into the larger puzzle of particle physics. It remains a powerful theoretical concept in search of a tangible identity. And then there's the question of the stop. What caused inflation to end so abruptly? The theory suggests that as this inflattened field decayed and dropped to a lower energy state, it released a tremendous amount of energy that flooded the universe, reheating it and populating it with the hot soup of particles that would eventually form atoms, stars, and us. This event is often called the Big Bang in popular science, but it's more accurately the moment the hot, dense universe we recognize began. But the mechanism behind this transition, this graceful exit, is still not fully understood. Did it happen everywhere at once or in a wave across the budding cosmos? Some theories even suggest that inflation may not have stopped everywhere, that it could be eternal, with pocket universes like ours constantly bubbling out of an ever-inflating background, giving a scientific twist to the idea of a multiverse. This single theory, born to explain smoothness, may ultimately predict an infinite diversity of worlds. This remarkable uniformity presents us with one of the most stubborn puzzles in cosmology, known as the horizon problem. To grasp why this is so baffling, we need to think about the most fundamental speed limit in the universe, the speed of light. Nothing, not even information or heat, can travel faster than light. This means that for two regions of space to have the same temperature, they must have been close enough together at some point in the past to exchange energy and reach a thermal equilibrium. They had to be within each other's cosmic horizon, the maximum distance light could have traveled since the beginning of time. Yet, when we look at the cosmic microwave background, we see that regions on opposite sides of the observable universe have the exact same temperature to a precision of 1 part in 100,000. The problem is, according to the standard Big Bang model, these two regions have never been in causal contact. There simply hasn't been enough time since the universe began for light or any form of energy to have traveled from one of these points to the other to even everything out. It's as if you walked into a vast auditorium filled with thousands of people, and you discovered that every single person, without having ever spoken to each other, had agreed to wear the exact same outfit down to the smallest detail. The coincidence is so perfect it defies logic, implying there must be a mechanism we're missing. This is where the theory of cosmic inflation provides its most elegant solution. Remember that period of hyper-exponential expansion? It tells us that the entire observable universe was, in fact, once an incredibly tiny subatomic volume. Every part of our vast cosmos was packed into a space so small that it was all easily within each other's horizon. This tiny region had more than enough time to mix thoroughly and settle into a perfectly uniform temperature, like a cup of coffee that has been stirred to an even warmth throughout. Then inflation happened. In that fleeting instant, this tiny, uniform patch was stretched by a factor of trillions upon trillions, becoming larger than our entire visible universe today. The smoothness and thermal equilibrium were simply frozen in by this incredible expansion and preserved across the immense scales we now observe. The horizon problem isn't a problem at all if the universe had this brief but dramatic growth spurt. It becomes a natural prediction. The two opposite sides of the sky appear the same because they were once intimately connected neighbors in a much denser cosmos. While inflation beautifully resolves the issue, it does lead us to a deeper, more subtle question about the precise nature of this thermal equilibrium. The cosmic microwave background isn't perfectly smooth. It contains those tiny, vital fluctuations that became the seeds for galaxies. The incredible precision of the overall uniformity suggests that the pre-inflation universe must have been in a state of exceptional thermal calm. How did it achieve this state? Was there some previous, even more ancient process that allowed this microscopic patch to become so perfectly mixed? The mechanism that established this initial equilibrium is still a topic of active research, a mystery hidden within the solution to another mystery. Furthermore, the success of inflation in solving the horizon problem relies on its specific timing and duration. The expansion had to start and stop in a very particular way to produce the universe we see. If it had ended a fraction of a moment sooner, the universe would have remained small and likely collapsed back on itself. If it had lasted a fraction of a moment longer, the universe would have been stretched so thin that no galaxies could ever have formed. This fine-tuning leads some scientists to wonder if the horizon problem is truly solved, or if we have simply replaced one enigma with another, shifting the question from how did the universe become uniform to why did inflation happen in such a perfectly orchestrated way? The answer may lie in a deeper understanding of the quantum fields that govern the universe's first moments, a realm where our physics is still feeling its way in the dark. But this perfectly smooth, uniform cosmos presents another, equally profound puzzle that has troubled cosmologists for decades. It's a problem of geometry, and it asks us to consider the very shape of the universe on the grandest of scales. Is space curved like the surface of a sphere, warped like a saddle, or is it fundamentally flat? For a long time, the answer seemed to require a level of fine-tuning so precise it bordered on the miraculous. This is known as the flatness problem. Imagine the density of the universe right after the Big Bang. There's a critical value for this density that acts like a cosmic balancing point. If the actual density were even slightly higher than this critical value, the force of gravity would have quickly pulled everything back together in a big crunch, causing the universe to collapse on itself long before any stars or galaxies could form. If the density were just a tiny bit lower, the expansion would have been so rapid that matter would have flown apart too quickly to ever clump together, resulting in a cold, dark, and eternally empty void. For our universe to exist as it does, full of structure and lasting for billions of years, the initial density had to be unfathomably close to that perfect critical value. How close? To within 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. To say the odds were stacked against us is a cosmic understatement. This incredible fine-tuning suggests that the universe we inhabit is exceptionally special, a notion that makes physicists deeply uncomfortable. Science seeks fundamental reasons, not incredibly lucky coincidences. It seemed as if the universe was born with its conditions set exactly right for life, with no explanation as to why. This is where cosmic inflation steps in once more, not just as a solution, but as a universe-making mechanism that naturally produces this flatness. The theory of inflation tells us that no matter what the original geometry of the universe was, whether highly curved or wildly warped, the period of hyper-fast expansion would have stretched the fabric of spacetime so dramatically that any curvature would be smoothed out. Think of it like taking a tiny, wrinkled piece of paper and enlarging it to the size of a continent. The tiny wrinkles become imperceptible, and the surface appears perfectly flat to anyone standing on it. Inflation does the same thing to the cosmos. It takes any initial curvature and flattens it by stretching space itself. This elegant solution transforms the flatness problem from a mystery of fine-tuning into a natural prediction. The universe isn't flat because it was born that way against all odds. It's flat because the process of inflation made it that way. It's a powerful and compelling answer. Yet, as with all great mysteries, solving one question often leads us to another, perhaps deeper one. While inflation explains how the universe became flat, it doesn't necessarily tell us why the underlying laws of physics allow for this critical density to exist in the first place. The value of the critical density is itself set by other fundamental constants, like the strength of gravity. This shifts the question of fine-tuning from the initial conditions of the universe to the fundamental laws that govern it. Why do these constants have the precise values that permit a flat, long-lived, and life-friendly universe? Is this just a happy accident within a vast multiverse where every possible value is realized somewhere? Or is there a deeper, yet-to-be-discovered principle that dictates these numbers? Furthermore, our measurements of the universe's geometry, while incredibly precise, are not absolutely perfect. data from missions like the Planck satellite confirm that the universe is flat too, within a margin of error of just 0.2%. But that tiny window of uncertainty still leaves room for fascinating possibilities. Could the universe have a very slight overall curvature that our current instruments cannot yet detect? And if so, what would that mean for our understanding of its ultimate fate? The flatness problem and its resolution through inflation ultimately points us toward the deepest questions about the laws of nature themselves and whether our cosmos is one unique possibility in a much vaster and perhaps stranger reality. But if inflation so elegantly explains the smoothness and flatness of our cosmos, you might wonder what concrete evidence compelled physicists to propose such a fantastical idea in the first place. The answer lies in the absence of something, a ghost from the earliest universe that should be everywhere but is mysteriously nowhere to be found. This is the case of the missing magnetic monopoles. To appreciate this puzzle, we need to take a quick detour into the nature of magnets themselves. Every magnet you've ever held, from a simple refrigerator magnet to a compass needle, has two poles, a north and a south. If you break that magnet in half, you don't get an isolated north and an isolated south. You simply get two smaller magnets, each with its own pair of poles. This seems to be a fundamental rule of nature, but our best theories of physics suggest this wasn't always the case. Grand unified theories, or GUT, are ambitious frameworks that attempt to describe how the four fundamental forces of nature were once united as a single, super force in the unimaginable heat of the early universe. These theories predict that as the universe expanded and cooled, it underwent a series of dramatic phase transitions, much like steam condensing into water or water freezing into ice. With each transition, a fundamental force would have frozen out and separated from the others. According to these JWSTs, one of the inevitable byproducts of the first and most dramatic of these splits would have been the creation of countless particles known as magnetic monopoles. Unlike ordinary magnets, a monopole would be a particle that carries only a single magnetic charge, either a north pole or a south pole, all on its own. They would be incredibly massive, stable, and indestructible relics from the dawn of time. The problem is, despite decades of searching with incredibly sensitive experiments, we have never found a single, definitive magnetic monopole. They should be as common as protons, a ubiquitous part of the cosmic landscape, yet they are utterly absent. This presented a massive crisis for particle physics and cosmology. If our grand theories correctly described the early universe, then these monstrous particles should be everywhere, and their overwhelming density and mass would have drastically altered the evolution of the cosmos, likely preventing the formation of galaxies altogether. Their conspicuous absence suggested that something was profoundly wrong with our models. This is where cosmic inflation emerged as a hero, offering an elegant solution to the monopole problem. Remember that period of hyper-fast expansion? It didn't just smooth out the universe, it effectively diluted the primordial monopole population to an undetectably low density. Think of it like this: imagine a single grain of sand in an entire desert. Now, imagine inflating that desert to the size of the observable universe. The chance of you ever stumbling upon that one specific grain of sand becomes essentially zero. Inflation did exactly that to the monopoles. It took any that were created in that initial hot phase and scattered them so far and wide across the cosmos that the average density in our observable patch of universe plummeted to nearly zero. Their absence isn't a failure of the grand unified theories. It's a stunning piece of evidence that a mechanism like inflation must have occurred, effectively sweeping the cosmic stage clean of these unwanted relics. However, as always, solving one mystery opens the door to another. The success of inflation in explaining the missing monopoles lends powerful support to the grand unified theories that predicted them in the first place. It suggests we are on the right track in our quest to unify the forces of nature. But it also raises a profound and tantalizing question. If these monopoles were created and then diluted away, do they still exist out there beyond our observable horizon? Could there be vast, distant regions of the multiverse where inflation did not occur, and the cosmos is instead dominated by a dense soup of these incredible particles, forever altering the physics of those alien realms? The absence of monopoles in our backyard is not just a clean-up story. It's a hint of a far wilder and more varied cosmic landscape than we can directly see, a silent echo of the unification of all forces in the universe's first fleeting moment of existence. But the smooth geometry and the missing relics of the early universe set the stage for an even more personal mystery, one that strikes at the very heart of our own existence. Consider this: according to all our fundamental laws of physics, the Big Bang should have created equal amounts of matter and antimatter. For every proton, there should have been an antiproton. For every electron, a positron. And in the fierce energy of that initial creation, these particles and antiparticles should have immediately sought each other out, annihilating upon contact in a brilliant flash of pure radiation, leaving behind a universe containing nothing but light. A cosmos with no stars, no planets, and certainly no one to wonder why. Yet here we are. Clearly something went differently. The fact that you and I and everything we see exists is proof of one of the greatest imbalances in nature. This is the profound puzzle of baryogenesis. Why does anything exist at all? This isn't a small statistical fluke. It's a fundamental asymmetry written into the fabric of reality. For the universe we know to have formed, for even a single atom to have survived the Great Annihilation, there had to have been an incredibly tiny but crucial excess of matter over antimatter. Scientists estimate that for every 1 billion matter-antimatter pairs that annihilated in the early universe, roughly one single particle of matter was left over. That 1 in a billion asymmetry is the source of every galaxy, every star, and every atom in our bodies. We are literally made from the leftover crumbs of a near-perfect cosmic cancellation. The question is, what physical process could have favored matter so slightly, yet so decisively? The quest for an answer leads us to a crucial concept known as CP violation. The C stands for charge conjugation, which is the act of swapping a particle with its antiparticle. The P stands for parity, which is like looking at the universe in a mirror, reversing all spatial coordinates. For a long time, physicists believed the laws of nature were perfectly symmetric under the combined operation of CP. That is, a universe made of antimatter should behave exactly like our matter universe when viewed in a mirror. The physics would be identical. But in 1964, experiments with neutral kaons, exotic subatomic particles, showed a slight breaking of this symmetry. The decay rates of these particles and their antiparticles were not perfectly identical. It was a monumental discovery, proving that nature does, on a subtle level, have a preferred handedness and can distinguish between matter and antimatter. This discovery was a crucial first step, earning its finders a Nobel Prize, but the amount of CP violation observed in these particle decays is far too small to account for the vast cosmic imbalance we see today. It's like finding a single dollar when you need to pay off a national debt. It's the right currency, but nowhere near enough. This has sent physicists searching for other, much stronger sources of CP violation in the hopes of solving the mystery. Their investigations point to the universe's first moments, a time of extreme energy when the fundamental forces we know today were still merged into one. One leading set of ideas falls under the umbrella of electroweak baryogenesis. This theory suggests that the asymmetry was created during the electroweak phase transition. This was a pivotal moment when the electromagnetic force and the weak nuclear force split apart as the universe cooled, much like water freezing into ice. If this transition was a first-order phase change, meaning it occurred through the formation and expansion of bubbles of the new phase in the old, it could have created the perfect conditions to tip the scales. These expanding bubbles would have been like walls of energy sweeping through space. Theorists propose that interactions of particles with these bubble walls could have preferentially created more matter than antimatter, especially if there are new, yet-to-be-discovered particles that exhibit much stronger CP violation than what we see in our current models. The hunt for these particles is a major driver behind experiments at the Large Hadron Collider. Other theories look even further back to an era of grand unification, when the strong nuclear force was also merged with the electroweak force. These grand unified theories naturally predict the existence of super-heavy particles known as X-bosons that could decay. If these decays also violate CP, they could have decayed slightly more often into matter than antimatter, planting the seed of asymmetry that later led to our entire cosmic structure. The magnetic monopoles we discussed earlier are actually predicted by many of these same GOTs, linking these two deep mysteries of the early universe together. There are even more exotic proposals, like the idea of a Fulkdyne baryogenesis, which involves hypothetical scalar fields in the early universe whose vibrations could have stored a tremendous asymmetry, later transferring it to the matter we know when they decayed. Or the possibility that the imbalance was generated through interactions with the inflattened field itself, weaving the origin of matter directly into the story of cosmic inflation. Each of these avenues of research is compelling, but none yet provide a complete and verified answer. The mystery of baryogenesis stands as one of the most significant open questions in physics because it is so deeply personal. It asks not just how the universe began, but how we came to be a part of it. Every atom in our bodies is a testament to a broken symmetry, a tiny deviation from perfect balance that had cosmic consequences. Solving it would require not just a deeper understanding of the cosmos's first moments, but a fundamental extension of our knowledge of particle physics itself, revealing new laws and perhaps new particles that hold the key to our own existence. Yet for all the matter that survived that great annihilation, for every atom that went on to form stars and planets, we have to confront a startling and humbling fact. It accounts for less than 5% of the total content of the universe. The grand structures we see, galaxies, clusters, and the vast cosmic web, simply would not hold together if the only gravitational glue were the atoms we know and love. Their gravity is far too weak. Something else, something invisible and mysterious, provides the overwhelming majority of the mass in the cosmos. This brings us to one of the most enduring and profound puzzles in all of modern science, the nature of dark matter. The story of its discovery begins not in the depths of space, but in the careful observations of the motions of galaxies within clusters. In the 1930s, a brilliant and unconventional astronomer named Fritz Zwicky was studying the Coma cluster, a massive group of galaxies. By measuring how fast these galaxies were orbiting the cluster's center, he could calculate the total mass needed to keep them gravitationally bound. The result was shocking. The mass required was hundreds of times greater than the mass that could be accounted for by all the visible stars, gas, and dust in those galaxies combined. Zwicky called this missing mass Dunkel Materie, or dark matter. For decades, his finding was largely dismissed as an anomaly, but the evidence became impossible to ignore decades later when astronomer Vera Rubin meticulously charted the rotation speeds of stars within individual spiral galaxies. If a galaxy's mass were concentrated in its bright central core, as we would expect, then stars on the outer edges far from the gravitational center should orbit much more slowly, just as Pluto orbits the Sun far more sluggishly than Earth. But that's not what Rubin found. Instead, stars at the very outskirts of galaxies were orbiting just as fast as those near the center. The only way this could happen is if each galaxy is embedded within a gigantic, massive sphere of something invisible, a halo of dark matter that extends far beyond the visible edge of the galaxy, providing the extra gravitational pull to whip those outer stars around. This invisible scaffolding doesn't just influence individual galaxies, It dictates the large-scale architecture of the entire universe. When we look at the cosmic microwave background, the subtle fluctuations in temperature are a frozen record of how matter was distributed in the very early universe. The patterns we see are a perfect match for a model where dark matter makes up about 27% of the cosmos, acting as the gravitational anchor around which normal matter could eventually clump and collapse to form the first galaxies. So what is this elusive substance? We know what it's not. It's not planets or black holes or clouds of regular gas and dust. All of those are made of baryons, the same protons and neutrons that make up our world, and we can account for them. Dark matter must be something entirely different. It does not interact with light or electromagnetic forces at all. It is completely invisible and transparent. It doesn't absorb, reflect, or emit any form of radiation we can detect. It only seems to interact with the universe through gravity. This means it can effortlessly pass through entire planets, and vast oceans of it are likely streaming through your body at this very moment without you ever feeling a thing. The leading theoretical candidate for what dark matter could be is a class of hypothetical particles known as WIMP, or weakly interacting massive particles. These particles would be heavy, perhaps hundreds of times more massive than a proton, and would interact with normal matter only through the weak nuclear force and gravity. This would explain their ghostly nature. For years, the hunt for WIMP focused on incredibly sensitive experiments deep underground, in abandoned mines and tunnels shielded from cosmic rays. The idea is that very rarely, a WIMP from the Milky Way's dark matter halo might bump into the nucleus of an atom in a vast vat of ultra-pure xenon or germanium, producing a tiny, telltale signal. Despite decades of searching with ever more sensitive detectors, these direct detection experiments have not found a single, unambiguous WIMP signal. This null result has led physicists to broaden the search, considering a whole zoo of other possibilities. Could dark matter be made of actions? These are incredibly light, wispy, hypothetical particles born out of theories trying to solve a different puzzle in particle physics. Their low mass means they would behave more like a pervasive, wave-like field throughout space. Or perhaps the answer lies not in a new particle, but in a modification of our fundamental understanding of gravity itself. Theories like modified Newtonian dynamics propose that on the incredibly large galactic scales, gravity behaves differently than Newton or Einstein predicted, eliminating the need for an invisible substance. However, these modified gravity theories struggle to explain all the observational evidence, particularly the way dark matter clearly separates from normal matter in the aftermath of colossal galaxy cluster collisions, which we've observed with telescopes like Hubble and Chandra. The true identity of dark matter remains one of the biggest unsolved problems in physics because it represents a fundamental gap in our understanding of the universe's composition. Its presence is felt everywhere, its gravitational hand guiding the formation of every structure we see, yet it remains utterly elusive to our direct perception. Unlocking its secret would not just solve a cosmic puzzle, it would open a door to a whole new realm of physics, revealing a hidden sector of particles and forces that have been shaping the cosmos since its very first moments. Yet as we grapple with the invisible gravitational pull of dark matter, we must confront an even more perplexing and dominant component of the cosmos, a force that doesn't pull but pushes. This is the mystery of dark energy, and while we observe its overwhelming effects today, its potential role in the universe's very first moments is one of the most speculative and fascinating questions in cosmology. We know dark energy as the enigmatic repulsive force causing the expansion of the universe to accelerate, making up a staggering 68% of the total energy budget of the cosmos. But could this strange energy have been active during the birth of the universe, playing a critical part in its initial formation? To explore this, we need to understand the peculiar nature of dark energy itself. Unlike matter or radiation, whose density decreases as the universe expands, dark energy appears to be a property of space itself. Its density seems to remain constant, meaning that as space grows, more dark energy appears to fill the void. This is why its effects have become dominant only in the last several billion years. For most of cosmic history, the universe was smaller and denser, with matter's gravity holding sway. But in the vast, empty reaches of our modern cosmos, the constant density of dark energy has allowed it to overwhelm gravity's pull, forcing the expansion to speed up. If this energy was present at the beginning, its behavior would have been dramatically different due to the incredible densities involved. One of the most thrilling speculations is that dark energy and the inflaton field, the driver of cosmic inflation, might be two sides of the same coin, or at least deeply related. Both phenomena involve a form of energy inherent to space that causes repulsive gravity and rapid expansion. The critical difference is one of scale and timing. Inflation was an incredibly powerful, ultra-short-lived event, while dark energy is an incredibly weak, persistent force that has only recently become noticeable. Could dark energy be the ashes of the inflaton field? Perhaps the inflaton field didn't completely vanish after reheating the universe, but decayed into a much weaker state that has lingered for billions of years, manifesting today as the dark energy we observe. This would beautifully link the universe's first instant with its ultimate fate. Another compelling idea is that dark energy could have influenced the very first quantum fluctuations that seeded all structure. If dark energy was present, even in a different form, its repulsive nature might have left a subtle imprint on the pattern of those primordial ripples. While our current observations of the cosmic microwave background align perfectly with models where inflation is the sole driver, next-generation telescopes might discover tiny anomalies, a slight statistical preference for certain sizes of fluctuations over others. That could be the fossilized fingerprint of an early dark energy component. Finding such evidence would revolutionize our understanding of the universe's dawn. There's also the radical possibility that dark energy is not constant, as our simplest models assume, but that it evolves over time. This idea, known as quintessence, proposes that dark energy is a dynamic field, slowly changing in strength. If that's true, then in the ultra-high energy environment of the early universe, this quintessence field could have been immensely powerful, potentially interacting with the inflaton field or even triggering the period of inflation itself. In this scenario, the same fundamental entity could have been responsible for the universe's dramatic birth and its accelerating death, a profound and poetic symmetry governing the entire cosmic timeline. Ultimately, the question of dark energy's early role pushes our theories to their absolute limits. It forces us to consider whether the two greatest mysteries of modern cosmology, the explosive beginning and the accelerating end, are intimately connected. Unraveling this connection may require a theory that successfully merges gravity with quantum mechanics, a theory of quantum gravity that can describe the universe at the moment of its creation. Until then, the potential that dark energy was a silent partner in the universe's first moments remains a captivating and open question, a reminder that the cosmos's deepest secrets are often hidden in plain sight, woven into the expanding fabric of space itself. But to truly grasp the sheer extremity of that first second, we need to push our minds even further back to the very limits of time itself. The Planck epoch represents the absolute frontier of human knowledge, a period from time 0 to approximately 10 to the power of -43 seconds after the Big Bang. This is not just a short time, it is a timescale so infinitesimally small that it is fundamentally meaningless in terms of our everyday experience. At this moment, the entire observable universe was compressed into a space of about 10 to the power of -35 meters across, a scale known as the Planck length. The energy densities and temperatures were so phenomenally high that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces are theorized to have been unified into a single primordial superforce. Our current pillars of physics, Einstein's general relativity, which governs the very large, and quantum mechanics, which governs the very small, completely break down under these conditions. Their equations produce nonsensical infinities, telling us that we lack a complete theory. To understand the Planck epoch, we need a theory of quantum gravity, a framework that can seamlessly marry these two contradictory visions of reality. This is the holy grail of modern theoretical physics, with candidates like string theory and loop quantum gravity offering tantalizing yet unproven glimpses into this mysterious origin point. It was a realm where the concepts of space and time as we know them may not have even existed, instead perhaps emerging from a more fundamental, foamy quantum geometry. As the universe expanded and cooled past this unimaginable threshold, it is believed to have entered the grand unification epoch, lasting until about 10 to the power of negative 36 seconds. Here, temperatures were still an incredible 10 to the power of 29 Kelvin, but just cool enough for gravity to decouple from the other three forces. This left the strong nuclear force and the electroweak force still united as a single, grand unified force. This era is dominated by the predictions of grand unified theories, which propose that all matter and energy were fundamentally equivalent. The universe was a seething, symmetric soup of exotic particles and radiation. It was during this epoch that the stage may have been set for baryogenesis, the creation of the matter-antimatter asymmetry. Many JWSTs predict that the decay of incredibly massive X-bosons, carriers of this unified force, would have slightly favored the production of matter over antimatter. Furthermore, this is the period when the magnetic monopoles we discussed earlier should have been copiously produced as topological defects when the unified force began to break. Their subsequent dilution by inflation is a key piece of evidence that this epoch truly occurred. The next great phase transition happened around 10 to the power of negative 36 seconds, marking the beginning of the electroweak epoch. As the name implies, this is when the strong nuclear force finally separated out, leaving only the electromagnetic and weak nuclear forces still unified. This epoch lasted for a surprisingly long time in the context of the early universe, all the way until 10 to the power of negative 12 seconds. While still an era of almost unimaginable energy, it is a regime that is slightly more accessible to our theoretical tools. The Higgs field, which today gives particles their mass, is thought to have been inactive at these high energies. This means that particles like quarks and electrons were massless and moved at the speed of light, behaving more like photons. The universe was a hot, dense plasma of these radiation-like particles. The electroweak force was mediated by massless particles, meaning there was no distinction between the photon and the W and Z bosons we know today. They were all part of a single family. It was only as the universe continued to cool and expand, finally dipping below a critical temperature of around 10 to the power of 15 Kelvin, that the Higgs field is believed to have undergone its own phase transition, often called the Higgs mechanism. This event is what broke the electroweak symmetry, giving the W and Z bosons their large masses while leaving the photon massless. This single act effectively created the distinction between the electromagnetic force and the weak nuclear force as we observe them now, and it bestowed mass upon the fundamental particles, a crucial step that would eventually allow them to clump together and form the first structures. What makes this first second so profoundly mysterious is that these are not events we can ever hope to recreate fully in a laboratory. The energies required are quadrillions of times greater than what our most powerful particle colliders can achieve. We are essentially forensic cosmologists, piecing together the clues left behind in the present-day universe, the elemental abundances, the patterns in the cosmic microwave background, the very existence of matter itself, to reconstruct a history of a time when the laws of physics were operating in a regime we can scarcely describe. Every step in this narrative, from the Planck scale to the electroweak transition, relies on extrapolating our known physics to its absolute breaking point and then venturing beyond with bold theoretical speculation. The first second was not a single event but a cascade of cosmic transformations, each one setting the immutable rules for the next, ultimately determining the fate of everything that was to follow. To push our understanding of the universe's birth to its absolute limit, we must venture into a realm so extreme that our very concepts of time, space, and causality cease to have meaning. This is the quantum gravity era, a period before the universe was even 10 to the negative 43 seconds old. At this incalculable instant, known as the Planck time, the cosmos was compressed into a volume of space so small it defies imagination. The Planck length, a scale a billion trillion times smaller than a single proton. The energy density was so immense that the temperature soared to an inconceivable 10 to the 32 degrees Kelvin. In this fiery crucible, the force of gravity, which we experience as a smooth, continuous force shaping planets and galaxies, was no longer a placid field. Instead, it was subject to the same wild, unpredictable quantum fluctuations that govern the subatomic world. This presents perhaps the most fundamental obstacle in all of theoretical physics, the clash between our two most successful and yet utterly incompatible descriptions of reality. On one hand, we have Einstein's general theory of relativity, a masterpiece that describes gravity not as a force, but as the elegant curvature of spacetime itself by mass and energy. It gives us a breathtakingly accurate picture of the cosmos on large scales, from the orbit of Mercury to the bending of light around black holes. On the other hand, we have quantum mechanics, which governs the bizarre, probabilistic world of the very small. It tells us that particles can be in two places at once, that empty space is a seething foam of virtual particles popping in and out of existence, and that certainty is replaced by probability. Both theories are magnificently powerful within their own domains, but they speak completely different mathematical languages. When we try to apply both to the extreme conditions of the quantum gravity era, the equations break down, producing nonsensical infinities that signal our models have hit a wall. The core of the conflict lies in the nature of spacetime itself. General relativity treats spacetime as a smooth, continuous stage upon which the drama of physics plays out. But quantum mechanics suggests that at the very tiniest scales, this stage cannot be smooth. It must be granular or quantized. Just as matter is made of discrete particles like electrons and quarks, perhaps spacetime itself is woven from fundamental atoms of space and time. In the quantum gravity era, these hypothetical quanta of spacetime would have been wildly fluctuating. The very fabric of the cosmos would have been a chaotic, foaming sea of uncertainty, with tiny wormholes tunneling in and out of existence and the geometry of reality shifting violently from one moment to the next. There was no before in any sense we would understand, because time itself may not have existed as a continuous flow. This is the ultimate frontier, a period that holds the keys to understanding the true origin of everything, yet it remains veiled behind a curtain we cannot yet lift. The quest to develop a theory of quantum gravity is the monumental scientific effort to pull back that curtain. The leading candidates, string theory and loop quantum gravity, approach the problem from radically different angles. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrations of these strings manifest as different particles and forces. Crucially, string theory naturally includes a particle called the graviton, which would mediate the force of gravity, seamlessly weaving it into the quantum framework. It suggests we live in a universe with more than the 3 spatial dimensions we experience, perhaps 10 or 11, with the extra dimensions curled up into a space too small to detect. In the quantum gravity era, these dimensions would have been unfurled, and the strings would have been vibrating with immense energy, defining the earliest structure of reality. Loop quantum gravity takes a more direct approach, focusing not on what matter is made of, but on spacetime itself. It proposes that space is not smooth, but is actually composed of a network of finite, woven loops, a spin network. The area and volume of space are quantized, meaning there is a smallest possible unit of space, a sort of pixel of reality. In this view, the Big Bang may not have been a singularity of infinite density at all, but a big bounce, a moment where a previous universe collapsed and then rebounded due to these quantum gravitational effects. During the quantum gravity era, this fabric of loops would have been intensely dynamic and jumbled, a primal state from which our familiar four-dimensional spacetime later crystallized. The challenge in testing these ideas is that the energy required to probe the Planck scale is astronomically beyond the reach of any conceivable particle collider. We are left to search for indirect evidence, faint echoes of this primordial chaos that might be imprinted on the cosmos. Some theories suggest that the quantum fluctuations of spacetime in this first instant could have left a subtle fingerprint on the polarization of the cosmic microwave background, a pattern we might one day detect with future observatories. Others propose that the granular nature of space might cause very high-energy photons from distant gamma-ray bursts to travel at slightly different speeds, an effect we could potentially measure. For now, the quantum gravity era remains a realm of beautiful, profound speculation. It represents the final boss in our video game of cosmic understanding, a level we have yet to reach where the very rules of the game were written. Unlocking its secrets wouldn't just complete our picture of the universe's birth, it would revolutionize our understanding of reality itself, from the smallest speck to the largest galaxy. But after all that unimaginable heat and density, after the forces separated and the matter somehow survived, the universe was still a completely opaque fog. For nearly 400,000 years, it was a searing, brilliant plasma, so dense that light couldn't travel more than a tiny distance before being immediately absorbed and scattered by a free electron. It was a constant, blinding flash, a universe trapped in its own incandescent glow. And then, in a cosmic moment that was both profoundly simple and utterly transformative, everything changed. This is the story of recombination and the release of the first light, an event that set the cosmic background for the rest of time. The key to this great transition was a drop in temperature. The universe had been expanding and cooling for millennia, and finally, it reached a critical threshold of around 3000 Kelvin. That's roughly half the temperature of the surface of our Sun, but for the particles in the early universe, it was a watershed moment. Up until this point, the universe was so energetic that atoms couldn't form. Electrons with their negative charge were routinely blasted away from the positively charged atomic nuclei by high-energy photons. It was a chaotic, ionized soup, but as the temperature fell, the energy of the photons dropped below the binding energy needed to keep electrons and protons apart. Suddenly, electrons could be captured by protons and helium nuclei, forming the first stable neutral atoms. This process is called recombination, which is a bit of a misnomer. It wasn't like electrons and protons were combining again. They were combining for the very first time into neutral entities. This had a monumental consequence for light. With free electrons suddenly captured into orbits around atoms, the road was cleared. Photons, which had been constantly bumping into these electrons, were suddenly set free. The universe, in an instant, went from being an opaque, glowing fog to a transparent, vast expanse. For the first time in history, light could travel in a straight line, and it's those very photons, stretched and cooled over billions of years, that we detect today as the cosmic microwave background. This first light didn't just illuminate the cosmos, it created a permanent snapshot of it. The moment of recombination froze a picture of the universe at the tender age of 380,000 years. The pattern of light we see is a direct map of the density of matter at that precise moment, and it is here that we find one of the most important discoveries in all of cosmology. The CMB is not perfectly smooth. It is imprinted with tiny variations in temperature, minute fluctuations on the order of 1 part in 100,000. These are the anisotropies, and they are the fossilized seeds of all structure in the universe. Those slightly denser regions, appearing as faintly warmer spots in the CMB, had just a little more gravitational pull. Over the eons that followed, they would slowly draw in more and more dark matter and gas, eventually growing into the vast cosmic web of galaxies and galaxy clusters we see today. The slightly less dense, cooler spots would become the great cosmic voids. The specific statistical pattern of these hot and cold spots is a treasure trove of information. By analyzing their size and distribution, cosmologists can precisely calculate the fundamental ingredients of the universe: the amount of ordinary matter, the density of dark matter, the influence of dark energy, and the overall geometry of space. It's like finding a perfectly preserved infant photograph of the cosmos and being able to read its entire genetic code, predicting its growth, its appearance, and even its ultimate fate. Yet for all it tells us, the cosmic microwave background still holds profound mysteries. The precise mechanisms that created those initial quantum fluctuations during inflation are still not fully understood. Furthermore, there are some large-scale anomalies in the CMB that continue to puzzle scientists, such as a curious cold spot that seems larger than our standard models can easily explain, and a puzzling alignment of fluctuations across the sky that some have whimsically called the axis of evil. These quirks might be statistical flukes, or they could be the first hints of entirely new physics, a glimpse of something that happened even before inflation, written in the faintest of whispers on this ancient canvas of light. It is our oldest family portrait, and we are still learning how to read every subtle detail in its faded, timeless image. But this newfound transparency, this cosmic dawn captured in the microwave glow, was not the universe's final form. That delicate, neutral fog of hydrogen gas, now bathing in the faint afterglow of recombination, would not last. A new upheaval was brewing, one that would take the dark, dormant cosmos and set it ablaze with light once more. This transformative period is known as the epoch of reionization, a slow-motion revolution that ripped apart the very atoms that had just found peace and ultimately shaped the universe into the brilliant, structured place we see today. For nearly 500 million years after the CMB was released, the universe entered what astronomers call the cosmic dark ages. With no stars or galaxies yet formed, space was filled with that expanding, cooling haze of neutral hydrogen and helium gas. It was an almost unimaginably vast and empty darkness, punctuated only by the fading whisper of the microwave background. Yet within this immense gloom, the gravitational seeds imprinted by inflation were silently at work. The slightly denser regions of dark matter were slowly, relentlessly pulling in that neutral gas. Over millions of years, these pockets grew denser and hotter until, in a spectacular climax, the pressure and temperature at their cores became so immense that they ignited the nuclear fusion of hydrogen. The very first stars in the universe were born, and what stars they were, known as population 3 stars, these firstborns were behemoths, thought to be hundreds of times more massive than our Sun. They burned at ferocious temperatures with a brilliant bluish-white light, and they lived fast and died young. Their immense size meant they exhausted their nuclear fuel in only a few million years, ending their short lives in catastrophic supernova explosions or by collapsing directly into massive black holes. But it was their intense radiation that served as the engine of reionization. These first stars did not just emit visible light, they flooded the cosmos with a torrent of extremely energetic ultraviolet photons. This ultraviolet radiation is incredibly potent. Each photon carries enough energy to rip an electron away from a neutral hydrogen atom, reionizing it and bringing the universe back to the opaque, plasma state it was in before recombination. But this time it was different. Instead of a hot, dense, uniform fog, this new ionization was happening in isolated pockets around the first stars and galaxies. Think of it like turning on lights in a gigantic, dark field one by one. Each of the first stars or early galaxies acted as a lone lighthouse, its powerful UV beam carving out a growing, transparent bubble in the surrounding neutral hydrogen fog. Over hundreds of millions of years, these individual bubbles grew larger and began to overlap, their edges meeting and merging, until the entire cosmic volume between galaxies was once again filled with a diffuse, ionized plasma. The universe had been reionized. This was not a quick or simple process, which is precisely why it remains such a fascinating mystery. We know it was largely complete by the time the universe was around 1 billion years old, but the specifics are still hotly debated. Was it driven primarily by the radiation from those first monstrous stars? Or did the black holes that formed from their deaths play an equally important role, as the superheated accretion disks around these early quasars poured out even more intense X-ray radiation? The latest observations from the James Webb Space Telescope are now peering back into this very era, searching for the faint signatures of these first galaxies. They are finding that early galaxies might have been more numerous and brighter than we predicted, suggesting they could have provided the critical radiation to complete this universal transformation without needing as many of the hypothetical population 3 stars. The significance of reionization cannot be overstated. It was the final major transition of the universe, the event that established the intergalactic medium in the transparent state it remains in today. This transparency is what allows us to see across such vast cosmic distances. Without it, the light from distant quasars and galaxies would be absorbed by a sea of neutral hydrogen, and our view of the cosmic depths would be completely obscured. The epoch of reionization didn't just light up the universe, it opened the curtains, granting every future generation of astronomers a clear window into the past. It was the moment the cosmos emerged from its dark, formative ages and took on the brilliant, structured appearance we recognize, setting the stage for the grand cosmic story that was still to come. These cosmic pioneers, known as population 3 stars, represent a ghost chapter in our galactic history. They were the universe's very first generation of suns, forged not from the ashes of previous stars like our own, but from the pristine, primordial elements that emerged directly from the Big Bang, pure hydrogen and helium. Without any heavier elements to help them cool and fragment, the collapsing clouds of gas that birthed them are theorized to have grown to absolutely monstrous proportions. We're talking about behemoths that could have been hundreds of times more massive than our Sun, burning at ferociously hot temperatures with a brilliant bluish-white light. Their lives would have been spectacularly short and violent, burning through their colossal fuel reserves in just a few million years before exploding as unimaginably powerful supernova or collapsing directly into massive black holes. The legacy of these first stars is written into the very fabric of our universe, yet we have never directly seen one. The reason is a matter of both distance and time. Their entire lifespan occurred during the cosmic dark ages, that period before the universe was fully reionized. Any light they emitted is now stretched by the expansion of the universe into the far infrared part of the spectrum, a wavelength that is incredibly difficult to detect. Furthermore, their ephemeral existence means they blinked out of existence billions of years ago. To find one would be like trying to spot a single, specific firefly that lit up for a few seconds on the first night of summer from an airplane flying over a continent months later. The task seems nearly impossible. Our strongest evidence for their existence is actually circumstantial, found in the chemical makeup of the oldest stars we can observe. In the halo of our own Milky Way, there exist ancient stars known as population 2 stars. These are nearly as old as the universe itself, and they contain only trace amounts of elements heavier than hydrogen and helium, what astronomers call metals. This severe lack of heavy elements is the crucial clue. the only way to forge these heavier elements like carbon, oxygen, and iron is through nuclear fusion in the hearts of stars or in the cataclysmic explosions of supernova. The fact that even these ancient stars have some metals suggests they formed from gas that had already been seeded by a previous generation. That first generation, the ones that did the initial seeding, had to be composed of pure hydrogen and helium. They had to be population 3. The hunt for these elusive giants is one of the primary missions of the James Webb Space Telescope. With its powerful infrared eyes, JWST is peering back to the very edge of the observable universe, to a time when the first galaxies were beginning to coalesce. While it may not spot an individual population 3 star, it is searching for their distinct signature. Scientists are looking for the unique chemical fingerprints in the light from incredibly distant galaxies, hoping to find systems that are completely devoid of heavy elements. Finding a galaxy that shows no signs of metals would be the next best thing to direct observation, a strong indicator that it is being lit solely by the fierce, short-lived light of the universe's very first stellar generation. Discovering them would be like finding the original ancestors of every star, planet, and living thing that has ever existed. Yet even as we search for the ghosts of the first stars, we must contend with the shadows they and their aftermath left behind, shadows that would eventually grow to dominate the centers of galaxies. This brings us to the enigma of the first black holes. How did these gravitational monsters, these regions of spacetime where gravity is so intense that not even light can escape, first emerge in the pristine dawn of the cosmos? And how did some of them grow so incredibly fast, reaching masses billions of times that of our Sun when the universe was less than 1 billion years old? This is a cosmic timing problem that challenges our understanding of physics. The leading theory points a finger directly at the demise of those first massive population 3 stars. As we discussed, these behemoths lived short, violent lives. When one of these stars, perhaps 200 or 300 times the mass of our Sun, reached the end of its brief few million years, it would have faced a cataclysmic fate. Its core, no longer supported by the outward pressure from nuclear fusion, would have collapsed under its own immense gravity. For the very largest of these pioneers, this collapse may have been so direct and complete that it bypassed a supernova explosion entirely, imploding directly to form a black hole. This is known as direct collapse. In an instant, a seed black hole would be born with a mass already dozens of times that of our Sun. This provides a straightforward, elegant origin story. The first stars die, and the first black holes are born from their ashes. However, there's a significant problem with this being the sole explanation: time. A black hole formed from a single star, even a huge one, would start with a mass of maybe a few hundred suns at most. To grow into a supermassive black hole weighing billions of solar masses within the first billion years of the universe, it would have to eat matter at a ferocious, nearly continuous rate, pushing up against the theoretical limits defined by physics. As matter falls into a black hole, it gets compressed and heated, emitting tremendous amounts of radiation. This radiation exerts an outward pressure that can actually push away the very gas the black hole is trying to consume, effectively putting a speed limit on how fast it can grow. This is called the Eddington limit. To reach supermassive sizes so quickly, these earliest black holes would have had to consistently feed at or above this limit for millions of years, a scenario that seems difficult to sustain. This is where a more exotic and dramatic origin story comes into play: the direct collapse black hole. Imagine not a star dying, but a vast, massive cloud of pristine hydrogen gas in the early universe collapsing under its own weight. In a typical gas cloud, as it collapses and heats up, the energy would eventually fragment it into many smaller clumps that go on to form a star cluster. But theorists propose that under very specific, pristine conditions, in a cloud largely devoid of heavy elements and without a lot of disruptive turbulence, something different could happen. Without heavy elements to help it cool efficiently, the cloud couldn't fragment. It would just keep collapsing, getting hotter and denser in its core until it reached a critical threshold. Then, fueled by a complex chain of molecular hydrogen reactions, it could potentially collapse directly into a black hole without ever forming a proper star first. This would create a truly monstrous seed from the very beginning, not a mere few hundred solar masses, but a behemoth tens of thousands of times the mass of our Sun, or even larger. This is a head start of epic proportions, a seed so massive that it could grow into a supermassive black hole within the available time without needing to break the rules of physics. The existence of these direct collapse black holes is still theoretical, but it provides a compelling solution to the puzzle of the early supermassive black holes we observe. The James Webb Space Telescope is now on the case, searching for the unique signatures of these objects. A direct collapse black hole would have a very distinct spectrum. It would be incredibly bright in ultraviolet light, but would lack the chemical fingerprints of heavy elements that are the telltale sign of a stellar environment. Finding such an object would be a monumental discovery, confirming a whole new pathway for the birth of cosmic giants. Regardless of their origin, these first black holes were not the end of the story, they were just the beginning. Once a seed was in place, whether from a star or direct collapse, it began its growth into the supermassive beings we see today. They feasted on the abundant gas that filled the early universe, and they likely grew even more rapidly through mergers, colliding with other black holes and combining their masses in violent events that sent ripples through spacetime itself. They became the anchors around which the first galaxies assembled, their immense gravity pulling in vast reservoirs of gas and shaping the formation of the very first stars. In a very real way, the evolution of galaxies and the growth of their central black holes are deeply intertwined, a cosmic dance that began in the earliest chapters of the universe and continues to this day. The mystery of the first black holes is not just about their birth, it's about understanding how they so quickly became the gravitational hearts of the cosmos, setting the stage for everything that was to follow. But these first stars and black holes were not isolated actors on a dark stage. They were the building blocks for the universe's first true cities of light, galaxies. The transition from a smooth, expanding universe to one filled with these vast, intricate structures is one of the great chapters in cosmic history. The story of how the first galaxies assembled is a grand tale of an invisible cosmic architecture sculpting the visible world. This process began with the most dominant yet elusive substance in the cosmos, dark matter. Following the blueprint imprinted by inflation's quantum fluctuations, dark matter began to clump together first. Its particles, unaffected by the pressure of light or the push of radiation, could start collapsing under their own gravity long before ordinary matter could. These gatherings of dark matter formed vast spherical halos, gravitational wells that acted as the foundational skeletons for everything to come. It was within these invisible, massive halos that the fate of primordial gas was decided. Ordinary matter, made of hydrogen and helium, was drawn by gravity into these dark matter potential wells, but unlike dark matter, this gas felt pressure. As it fell inward, it heated up, and it could also be pushed around by the intense radiation from the first stars and black holes. In the earliest, smallest halos, this was a real problem. A nearby supernova or a burst of radiation from a young quasar could easily blast the gas right back out, preventing a galaxy from forming altogether. But as the dark matter halos grew larger through mergers and by accreting more material, their gravitational grip became stronger. Once a halo reached a critical mass, its pull was simply too powerful for the gas to resist or for external radiation to disrupt. The gas would plunge into the center, cool by radiating away its heat, and finally, catastrophically collapse to form the first generation of stars in earnest, birthing the first true dwarf galaxies. What is truly astonishing is the speed at which some of these early galaxies seem to have formed. observations from the James Webb Space Telescope are revealing galaxies that appear massive and mature at a time when the universe was only a few 100 million years old. This presents a fascinating challenge to our models. How could such large structures assemble so quickly? The answer may lie in the unique environment of the early universe. At that time, the density of matter was much higher, and the dark matter halos that were the sites of galaxy formation were packed closer together. This allowed for an extremely rapid and efficient period of merger and growth. Small protogalaxies could collide and combine into larger ones at a rate far exceeding what happens in the more spread-out modern universe. It was a violent, chaotic, and incredibly productive period of cosmic construction. The properties of these infant galaxies offer us a direct window into the conditions of the early cosmos. Many of them appear to be incredibly compact and turbulent, with star formation rates that put our own sedate Milky Way to shame. They were likely blob-like and irregular, lacking the beautiful spiral arms or elliptical shapes we associate with modern galaxies. Those elegant forms would emerge later through mergers and billions of years of evolution. Crucially, their chemical makeup tells a clear story. The first galaxies to form would have had very low metallicity, meaning they contained almost no elements heavier than helium. As successive generations of stars within them lived and died in supernova explosions, they polluted their galactic environment with newly forged elements like carbon, oxygen, and iron. So, by measuring the metallicity of an ancient galaxy, astronomers can effectively determine its generational age. A galaxy with barely any heavy elements is a true first-generation system, a cosmic fossil whose stars are made of almost pure primordial material. Studying these pioneers helps us answer fundamental questions about structure formation itself. Their sheer existence and early maturity provide strong support for the lambda-cold dark matter model of the universe, confirming that dark matter is indeed cold, meaning its particles moved slowly in the early universe, allowing it to clump effectively on small scales and form the seeds for galaxies. The distribution of these early galaxies across the sky also holds clues. If they are found to cluster in ways that our models don't predict, it could point to something new about the nature of dark matter or the properties of those initial inflationary fluctuations. Every faint red smudge of light detected by JWST from the cosmic dawn is not just a picture of a galaxy. It's a data point in the universe's origin story, a vital piece of evidence in our quest to understand how a smooth, hot beginning gave rise to the intricate, structured cosmos we inhabit today. So if dark matter provided the scaffolding and gravity did the heavy lifting, why did the universe remain shrouded in darkness for so long after the Big Bang? We arrive at a pivotal moment in cosmic history, a period of waiting known as the Cosmic Dark Ages. This wasn't a sudden event, but a slow, patient simmering that lasted for nearly 200 million years. The universe had all the ingredients for starlight, vast clouds of hydrogen and helium gas, and the gravitational seeds from inflation, and yet nothing ignited. This delay, this long pause before the dawn, is a mystery that tells us the early cosmos was a place of subtle balances and fierce opposition. The formation of the very first stars was not a simple matter of gravity pulling gas together. It was a dramatic battle against forces that actively worked to prevent it. To understand the delay, we must first appreciate the state of the universe after recombination. Once the cosmic microwave background radiation was released, the cosmos was filled with a warm, diffuse fog of neutral hydrogen gas. This gas, while primed to collapse under gravity, had a major problem. It was incredibly inefficient at cooling down. For a cloud of gas to collapse and form a star, it must be able to shed the heat and energy generated by its own gravitational contraction. If it can't cool, the internal pressure builds and fights back against the collapse, creating a stalemate. In our modern universe, this isn't an issue. Giant molecular clouds are filled with dust grains and heavy elements like carbon and oxygen. which are fantastic at radiating heat away in the form of infrared light. This efficient cooling allows the cloud to fragment and collapse into stars, but the first gas clouds were different. They were pristine, composed only of hydrogen and helium, elements that are notoriously poor at cooling at the temperatures present in those early halos. The primary coolant available was molecular hydrogen, or H2, which can emit radiation through a slow, inefficient process when it gets jostled and vibrated. This was like trying to cool a massive engine with a single, tiny ice cube. This cooling bottleneck was the first great delay. For a protogalactic cloud to finally collapse and form that first generation of population 3 stars, it had to rely on this sluggish molecular hydrogen cooling. This process required the gas to reach a certain density and for the dark matter halo housing it to grow to a critical mass, a threshold of about 100,000 to 1 million times the mass of our Sun. Only halos of this size could generate a gravitational pull powerful enough to compress the gas to the point where H2 cooling could become even marginally effective. Reaching this mass took time. The smaller dark matter halos formed first, but they were simply too weak to overcome the gas pressure and the disruptive influences around them. They had to merge and accumulate more mass over hundreds of millions of years of cosmic time, and those disruptive influences were formidable. The early universe, though dark, was not a peaceful place. The feeble starlight that did eventually manage to form became its own worst enemy. The first stars and protogalaxies were not just producers of light, they were prodigious sources of Lyman-Werner radiation, a specific band of energetic ultraviolet photons. This radiation has a devastating effect on the primary coolant, molecular hydrogen. When a Lyman-Werner photon strikes an H2 molecule, it can break it apart, dissociating it back into plain atomic hydrogen. This process, known as photodissociation, effectively destroys the very mechanism that allows new stars to form. So the first small galaxies that did manage to ignite would have immediately begun blasting their surroundings with this destructive feedback, sterilizing nearby regions of space and preventing their neighbor halos from forming stars. This created a self-regulating cycle where the birth of the first stars actively suppressed the birth of the next generation, effectively limiting the star formation rate and prolonging the dark ages. This complex interplay between gravity, cooling physics, and radiative feedback created a universe-wide delay. The ignition of the first stars wasn't a single, sudden switch being flipped everywhere at once. It was a slow, gradual process that began in the rarest, densest peaks of the dark matter distribution, the places that reached the critical mass threshold first, and then slowly propagated outward. The timing, around 200 to 400 million years after the Big Bang, represents the point when the largest number of dark matter halos had finally grown massive enough to overcome the cooling bottleneck and withstand the damaging radiation from their luminous neighbors. It was the moment the balance finally tipped and the universe, after a long and quiet gestation, could truly begin to shine. Yet even as we map the grand structures born from those first stars, we must turn our attention to the very atoms that built them and to a stubborn numerical discrepancy that has challenged our models for decades. After the universe had expanded and cooled for just a few minutes, the conditions became perfect for the first atomic nuclei to form from the primordial soup of protons and neutrons. This brief, explosive period is known as Big Bang nucleosynthesis, and it was incredibly successful at forging the lightest elements. The calculations from this era beautifully predict the observed cosmic abundances of hydrogen and helium, a triumph that serves as a cornerstone of the Big Bang theory. But there is a glaring exception, a single element whose predicted amount simply doesn't match what we see in the oldest stars. This is the curious case of the lithium problem. According to our meticulous models of those first 3 minutes, the nuclear reactions should have produced a specific, measurable quantity of lithium-7, the most common isotope of this light metal. The laws of physics, as we understand them, point to a clear expectation. Yet when astronomers look at the atmospheres of the most ancient stars in the halo of our Milky Way, stars that formed from nearly pristine material and have changed little since the dawn of time, they find only about 1/3 of the predicted lithium. It's not a small margin of error. It's a factor of 3 discrepancy that has persisted despite increasingly precise observations and refined theoretical calculations. This isn't just a minor accounting error, it's a fundamental puzzle. If our understanding of the first few minutes is so precise for hydrogen and helium, why does it fail so noticeably for lithium? The search for a solution has led physicists and astronomers down several fascinating paths. One possibility is that our understanding of the nuclear physics itself might be incomplete. The predicted amount of lithium is highly sensitive to the rates of specific nuclear reactions that occurred during that frantic 3-minute window. Perhaps there is a previously unknown nuclear reaction pathway that destroyed lithium-7 as it was being formed, or maybe the cross-sections which measure the probability of these nuclear interactions, for key reactions are slightly different than what we've measured in laboratories here on Earth. Scientists have scrutinized these reaction rates with immense care, but the possibility remains that some subtle quantum effect, only significant under the extreme conditions of the early universe, could account for the missing lithium. Another compelling line of inquiry suggests that the lithium might have been destroyed after Big Bang nucleosynthesis ended, but before the oldest stars we observe had formed. During the hundreds of millions of years of the cosmic dark ages, this primordial lithium would have been drifting through the universe. Could it have been processed or depleted by some unknown astrophysical process? Perhaps the first population Roman 3 stars, those immense and short-lived giants, consumed or altered the lithium in their environments before they exploded, effectively scrubbing it from the gas that would later form the ancient stars we study today. Or maybe the lithium sinks into the interiors of these old stars, becoming diluted and hidden from our view over billions of years through various mixing processes. There are even more exotic proposals that look beyond the standard model of particle physics. Could the presence of unknown types of particles have influenced the nuclear reactions? For instance, if a type of exotic particle, such as a negatively charged supersymmetric particle, existed in the early universe, it could have formed temporary atoms with nuclei, effectively changing their size and altering the rates at which they fused with other nuclei. This could have provided a novel channel to suppress the production of lithium-7 without disrupting the successful predictions for the other elements. While speculative, such ideas highlight how a small anomaly like the lithium problem can become a window into potentially revolutionary new physics. The persistence of this mystery serves as a powerful, humbling reminder. It shows that even our most well-tested and successful models of the cosmos can still hold surprises. The lithium problem is a small but persistent crack in the otherwise solid edifice of Big Bang cosmology, and scientists continue to chip away at it, using ever more powerful telescopes to measure lithium in increasingly ancient stars and running sophisticated simulations to test every conceivable solution. It demonstrates that the universe's first few minutes, though seemingly simple and governed by well-known physics, may still conceal secrets waiting to be unraveled. Yet, even as we piece together the history of the cosmos from the light of ancient stars and the whisper of the microwave background, there is a deeper, more fundamental signal we have been striving to detect, a tremor from the very instant of creation itself. This brings us to one of the most profound and technically daunting quests in all of cosmology, the hunt for primordial gravitational waves. These are not the ripples in space-time from colliding black holes that LIGO has detected in the modern universe. These are something far grander and more ancient. They are the hypothesized echoes of the Big Bang, the literal shaking of the fabric of reality caused by the universe's explosive birth and its subsequent period of hyper-fast inflation. To understand why these waves are such a holy grail for physicists, we need to consider what generated them. The theory of cosmic inflation proposes that the universe underwent a period of incredibly rapid expansion, blowing up by a factor of trillions in a vanishingly small fraction of a second. Such a violent, energetic event would have been more than enough to violently stir the very substrate of space-time, sending powerful gravitational waves ringing out through the newborn cosmos. Unlike the gravitational waves from black hole mergers, which are like small, specific splashes in a pond, these primordial waves would be a vast, universe-filling tsunami, a permanent background hum of space-time vibration left over from the beginning. Their unique signature would be imprinted on the oldest light we can see, the cosmic microwave background. This is where the connection becomes truly elegant. We've already seen how the CMB carries a temperature map, the faint hot and cold spots that are the seeds of galaxies. But light has another property called polarization. As the light from the early universe traveled through this sea of primordial gravitational waves, the waves would have subtly stretched and squeezed space-time, affecting the direction in which the light's electric field vibrates. This process would have created a very specific curl-like pattern in the polarization of the CMB light, known as B-mode polarization. Finding this distinct swirling pattern is considered the smoking gun for inflation because no other known process in the later universe could create a signal like it across the entire sky. It would be direct, incontrovertible evidence that the universe really did undergo this fantastic growth spurt. The potential discovery is so monumental that teams of scientists have dedicated decades and built incredibly sensitive instruments to search for it. Projects like the BICEP and Keck arrays at the South Pole and the Simons Observatory are essentially looking for this faint, swirling fingerprint on the CMB. The South Pole provides one of the clearest, driest views of the sky on Earth, which is crucial because atmospheric moisture can easily obscure this incredibly subtle signal. These telescopes are not looking at visible light. They are designed to detect the precise polarization of microwaves, measuring differences in temperature on the scale of millionths of a degree. The technical achievement is staggering, requiring them to filter out confounding signals from our own galaxy, such as dust that can also polarize light in a similar way. What makes this mystery so captivating is that the search is a two-way street. Detecting these primordial B-modes would be a landmark victory, confirming our boldest ideas about the universe's first moments. But their absence is equally, if not more, revealing. If continued, more sensitive searches ultimately find no evidence of these primordial gravitational waves, it would force a massive and thrilling rethink of early universe physics. It wouldn't necessarily mean inflation is wrong, but it would strongly suggest that it occurred at a much lower energy scale than many of the most popular models predict. This would immediately rule out a whole class of grand theories, particularly many grand unified theories that require high-energy inflation to work. It would push physicists toward more exotic and nuanced ideas, perhaps involving multiple fields driving inflation or even alternatives to inflation altogether. The silence of the cosmos would be speaking just as loudly as a detected signal, guiding us toward a new understanding of how everything began. This hunt is not just about finding proof, it's a fundamental conversation with the universe, and we are waiting with bated breath for its reply. But just as we are learning to read the universe's oldest light, a startling discrepancy has emerged, one that strikes at the very heart of our cosmic measurements and threatens to unravel our most fundamental understanding of how the cosmos works. This is the Hubble tension, and it is arguably the most significant and perplexing problem in modern cosmology. At its core, it's a story about a single number, the Hubble constant, which represents the current expansion rate of the universe. For decades, astronomers have worked to pin down this number with ever-increasing precision. The shocking revelation is that we now have two incredibly precise, yet completely incompatible, ways of measuring it, and they stubbornly refuse to agree. The first method looks at the local, modern universe. Astronomers use what's known as the cosmic distance ladder. They start with reliable, well-understood objects relatively close to home, like Cepheid variable stars. These stars pulsate at a rate that is directly tied to their intrinsic brightness. By measuring their pulsation period, astronomers can determine their true brightness, and by comparing that to how dim they appear from Earth, they can calculate a precise distance. They then use these Cepheids to calibrate the distance to even brighter mile markers, like Type Ia supernova. These supernovae are phenomenal because they all explode with nearly the same peak brightness, making them visible across billions of light years. By observing how fast these distant supernovae are moving away from us, their redshift, and knowing their precise distance, scientists can calculate the Hubble constant. This is a direct, empirical measurement of the universe's current expansion rate. After years of meticulous work, led by teams like the one using the Hubble Space Telescope, this local measurement has converged on a very specific value. The second method looks back to the infant universe, to the cosmic microwave background. The Planck satellite spent years mapping the faint temperature fluctuations in this afterglow with exquisite detail. These fluctuations are a frozen record of the density variations in the early cosmos. By applying our extremely well-tested model of the universe's evolution, the lambda cold dark matter model, cosmologists can run the clock forward from that infant state to predict what the Hubble constant should be today. This is not a direct measurement of the current expansion. It's a prediction based on the physics of the early universe and our model of how it evolved. The Planck collaboration's prediction is also incredibly precise. Here's the crisis: these two numbers disagree. The measurement from the local universe suggests a faster expansion rate, while the prediction from the early universe suggests a slower one. The gap between them is not a small statistical fluke that can be brushed aside. It is a significant difference of several kilometers per second per megaparsec, with an error margin so small that the probability this is just a mistake is less than 1 in a million. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths every single time. This isn't just a tension, it's a full-blown discrepancy that has withstood over a decade of intense scrutiny, improved measurements, and attempts to find hidden errors. This leaves cosmologists with a thrilling and unsettling possibility. The problem isn't with our measurements, but with our model. The lambda CDM model, which has been spectacularly successful at explaining so much of what we see, might be incomplete. The Hubble tension could be the first observable crack in its foundation, pointing to new physics that operated in the early universe and whose effects are only becoming apparent now. Perhaps dark energy isn't a constant after all, but an evolving force that has changed strength over time. Maybe there is a new type of dark radiation or an interaction between dark matter and dark energy that we haven't accounted for. Some theorists have even proposed more exotic ideas, like the existence of an early dark energy that briefly surged during the universe's first few 100,000 years, subtly altering the sound waves imprinted on the CMB and throwing off the prediction for today's expansion rate. Others wonder if the very fabric of space-time could have properties we don't yet understand, or if there is something unique about our local region of space that makes it an outlier. Resolving the Hubble tension is now a primary goal for the next generation of observatories, from the James Webb Space Telescope, which is already verifying the local distance ladder with breathtaking precision, to new telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, which will provide a torrent of new data. They will either find a hidden systematic error, or they will confirm the discrepancy and finally force us to rewrite the textbooks. This isn't a crisis to be feared, it's an opportunity. It is the universe presenting us with a profound puzzle, a clue that our current understanding is good but not complete. The Hubble tension is our guiding star, pointing the way toward a deeper, richer, and more surprising theory of everything. Yet for all the grand success of the cosmic microwave background in confirming our standard model of the universe, it holds a peculiar and persistent anomaly that some cosmologists have, with a hint of dramatic flair, nicknamed the axis of evil. This isn't a cosmic superweapon, but something almost as unsettling to a scientist, a mysterious and unexpected alignment in the oldest light we can see that seems to point directly at us, challenging the foundational principle that we do not occupy a special place in the cosmos. The story begins with the incredibly detailed all-sky map of the CMB produced by satellites like Planck. When cosmologists analyze this map, they don't just look at the hot and cold spots, they study the patterns and correlations between them. According to our most cherished cosmological principle, the universe should be isotropic and homogeneous on the largest scales. This means it should look roughly the same in every direction, with no preferred axis or special center. The fluctuations in the CMB should be completely random and evenly distributed, like the random static on an old television set. But when scientists subtract out the dominant expected patterns, they are left with some strange, faint, large-scale anomalies. The most famous of these is an apparent alignment. This alignment has two puzzling aspects. First, the larger scale fluctuations on one side of the sky seem to be correlated with those on the opposite side in a way that suggests a preferred direction or an axis running through the universe. Second, and even more bizarrely, this hypothetical axis is eerily aligned with the plane of our own solar system and the direction of the sun's motion through the galaxy. It's as if the universe's grandest blueprint has a faint arrow that just happens to be pointing at our doorstep. The probability of this happening by pure chance is extremely low, which is why it demands an explanation. Scientists have proposed a number of solutions ranging from the mundane to the revolutionary. The most conservative explanation is that this is simply a statistical fluke. When you analyze a massive dataset like the CMB, you're bound to find some strange-looking patterns purely by random chance. It's the cosmological equivalent of seeing a face in the clouds. Another possibility is that the anomaly isn't in the cosmos at all, but in our own backyard. Perhaps there is some unknown local contaminant we haven't fully accounted for. Maybe dust within our own solar system or galaxy is imparting a subtle, structured glow that we're mistakenly interpreting as part of the primordial CMB signal. The hunt for such a foreground contaminant is ongoing, but so far, nothing has been found that can fully explain the effect. If the alignment is real and not an illusion, the implications are profound. It could mean that our universe is not isotropic on the largest scales, which would force a radical rewrite of the cosmological principle and our standard model. Some speculative theories have attempted to incorporate this, suggesting the universe might be slightly anisotropic, like a giant cosmic egg, stretched more in one direction than others. Others have proposed even more mind-bending ideas, such as the universe being finite and having a complex, multiply-connected topology like a video game where if you go off one edge of the map, you reappear on the other. In such a universe, light could wrap around, creating correlations that make it appear as if there's an axis or a preferred direction. The name axis of evil itself, while catchy, reflects the deep discomfort this anomaly causes. It's evil because it threatens the very foundations of modern cosmology, the principle that we are not in a privileged location. If the largest structures in the universe are somehow aligned with our insignificant little solar system, it would suggest a return to a pre-Copernican idea, placing us back at the center of the cosmos in a way that makes physicists deeply uneasy. For now, the axis of evil remains an unsolved mystery, a tantalizing and faint whisper in the data that neither goes away nor finds a comfortable explanation. It stands as a reminder that even our most successful theories might be incomplete, and that the universe may still have profound surprises in store, hidden in the subtle patterns of its first light. After journeying through these grand cosmic mysteries, from the first spark of light to the formation of galaxies, we arrive at a question that is perhaps the most personal and haunting of all. Where is everybody? The universe is unimaginably old and vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which are now known to host planets. The numbers suggest a cosmos teeming with potential, and yet when we listen, all we hear is a profound and unsettling silence. This is the Fermi paradox, often called the Great Silence, and it leads us to wonder if the early universe itself might have set the stage for a cosmos that is, for all its splendor, overwhelmingly lonely. One compelling line of thought suggests that the answer might be written in those first chapters of cosmic history. Perhaps the conditions necessary for intelligent life are not just about being in the right place at the right time, but about being in the right place at the only time. The very early universe was a hostile and volatile place. For hundreds of millions of years, it was devoid of the heavy elements essential for building rocky planets like Earth and complex chemistry. The first stars, those immense population Roman III giants, lived and died in spectacular supernovae, seeding the cosmos with the first carbon, oxygen, iron, and other elements of life. But this process took time. Generations of stars had to be born and die to enrich the interstellar gas with enough metals to form terrestrial planets. This suggests there may have been a sweet spot for the emergence of life, a window of opportunity that opened after a certain level of metallicity was achieved, but before the universe changed in ways that made life more difficult. What if we are among the very first? This concept, known as the early bird hypothesis, proposes that the vast majority of life-friendly planets are still in their future. We might be a premature civilization in a galaxy that is still mostly young and unsettled, one of the first whispers in a cosmos that is only just waking up to the possibility of consciousness. On the other hand, the Great Silence could point to a much darker possibility, that the window for life is not just early, but incredibly narrow. The universe may be filled with the ruins of civilizations that rose and fell long before we ever looked up at the stars. This is the concept of a great filter, a hypothetical barrier that is so difficult to overcome that it prevents almost all life from progressing to the point of interstellar communication or travel. The terrifying question is, where is this filter located? Is it behind us, something we have already passed, making us a miraculous anomaly? Or is it ahead of us, a looming catastrophe that inevitably destroys all advanced civilizations? If the filter is behind us, it could be one of the incredibly rare steps that occurred in our own past. Perhaps the transition from simple prokaryotic cells to complex eukaryotic cells. An event that took over 1 billion years to happen on Earth is astronomically improbable. Or maybe the filter was the specific conditions that allowed for the development of technological intelligence itself. If the filter is ahead of us, the possibilities are grim. It could be that advanced technology inevitably leads to self-destruction through war, environmental collapse, or a mishap with powerful experiments. Or perhaps there is something out there that makes silence the only safe option for a civilization that wishes to survive, a lurking danger that encourages every intelligent species to hide. Then there is the possibility that we are simply looking in the wrong way, like someone trying to have a conversation using a telegraph machine in the age of fiber optics. Our search for extraterrestrial intelligence, or SETI, has primarily focused on a narrow slice of the electromagnetic spectrum, listening for deliberate radio signals. But what if advanced civilizations have moved far beyond such primitive technology? They might communicate using neutrinos, gravitational waves, or something we haven't even discovered yet. Their artifacts might not be giant radio beacons, but something subtler, like cloaked probes in our own solar system or megastructures around distant stars that we are only just learning how to detect. We are like islanders on a remote shore, looking for smoke signals while the rest of the world is using the internet. Ultimately, the Great Silence forces a kind of cosmic introspection. It asks us to consider our place in the universe not just spatially but temporally. Are we pioneers, survivors, or simply unaware? The answer might be found by looking back at the very beginning, to the specific physical constants and initial conditions that made our existence possible. The silence may not be an absence, but a message, a clue that the journey from the Big Bang to a conscious brain able to ponder its own origins is a chain of events so fragile and improbable that we might truly be alone, the universe's first and only way of understanding itself. This brings us to a cosmic case of missing matter, a discrepancy that strikes at the very heart of our understanding of how galaxies are built. It's known as the missing satellites problem, and it begins with one of the most powerful tools in a cosmologist's arsenal, the supercomputer simulation. When scientists program our best models of the universe, including the precise amount of cold dark matter and the initial conditions from the cosmic microwave background, and let them run, they produce a universe that looks remarkably like our own. Vast cosmic webs form and grand spiral galaxies emerge, but there's a curious detail. These simulations predict that a galaxy like our Milky Way shouldn't be alone. It should be surrounded by a vast entourage, a swarm of thousands of smaller dark matter clumps. These are the remnants of the first structures to form, the small building blocks that never merged into larger galaxies. They should be everywhere, yet when we look up at the sky and count the actual dwarf galaxies orbiting our own, we find only a few dozen. It's a dramatic mismatch between theory and observation, a puzzle that has forced astronomers to ask a profound question: where did all the missing galaxies go? To appreciate why this is so puzzling, we need to understand what these dark matter clumps represent. In the cold dark matter model, the first structures to collapse under their own gravity are the smallest ones. Think of it like a rain shower. The first puddles to form are the smallest, and only later do they merge into larger pools and lakes. The universe should be filled with these tiny, primordial puddles of dark matter. Each of these clumps or halos is a potential site for a dwarf galaxy. If there's enough gas pulled into the halo, and that gas can cool and condense, it should ignite stars and become a visible satellite. Our simulations are very confident about the sheer number of these dark matter halos. They are a natural and robust prediction of the model. So the fact that we see a sky that is far emptier than the simulations suggest means one of two things. Either the dark matter halos are there but for some reason didn't form stars and are completely invisible, or there's something fundamentally wrong with our understanding of dark matter or structure formation. This has led scientists down two primary paths to solve the mystery. The first and most promising solution involves a process called reionization. Remember that period when the first stars and galaxies flooded the universe with energetic ultraviolet radiation. That event may hold the key. The idea is that those thousands of small dark matter halos did indeed form and began to pull in gas, but they were extremely low mass, meaning their gravitational grip was very weak. When the cosmic floodlights of reionization switched on, the intense UV radiation would have heated the gas in and around these tiny halos to immense temperatures. This heated gas would have gained enough energy to simply evaporate away, escaping the feeble gravity of the small halo forever. Without a reservoir of cool gas, star formation in these halos would have been stifled before it could even begin. They would have become dark, starless ghosts, invisible clouds of dark matter with no stars to mark their location. In this scenario, the simulations are right about the dark matter, but they need to better account for the devastatingly efficient sterilizing effect of early radiation on the smallest structures. The second path to a solution is more radical. It questions the very nature of dark matter itself. The standard model assumes cold dark matter, meaning the particles move slowly and clump easily on small scales. But what if dark matter is not completely cold? What if it's slightly warm? Warm dark matter would consist of particles that are much lighter and faster moving. This slight warmth would have a dramatic effect. It would smooth out the universe on small scales, preventing those myriad tiny dark matter clumps from ever forming in the first place. The number of small halos predicted would plummet, potentially bringing the theory into much closer alignment with the number of dwarfs we actually see. While this is an elegant solution, it faces its own challenges, as it might also suppress the formation of the very first galaxies in a way that might conflict with new James Webb Space Telescope observations. The hunt is on for any observable signature that could distinguish between a universe filled with cold dark matter halos that are mostly dark and one where warm dark matter prevents them from existing at all. The fascinating twist is that we may have already found evidence for the first solution, the dark, starless halos. Astronomers have discovered a number of ultra-faint dwarf galaxies orbiting the Milky Way. These are so dim they contain only a few hundred stars, and they are dominated overwhelmingly by dark matter. They are essentially visible tips of a vast iceberg of dark matter halos. The existence of these faint, hard-to-detect objects suggests that there could indeed be a whole population of even darker halos, ones that manage to capture a tiny wisp of gas and form a handful of stars, or perhaps none at all. The next generation of telescopes will be crucial in this search, looking for the faintest possible star clusters or even using indirect methods to detect the gravitational influence of completely dark halos as they drift through the galaxy. The missing satellites problem is no longer seen as a fatal flaw in our model, but rather as a powerful clue. It's guiding us toward a more nuanced understanding of the complex interplay between dark matter and the ordinary matter that lights up the cosmos, revealing a history where the first starlight didn't just illuminate the universe, it also decided what would remain forever in the dark. But the challenges of mapping the dark matter scaffolding don't end with simply counting missing satellites. They extend deep into the very heart of these cosmic structures, into a puzzle concerning their internal architecture. This enigma is known as the cuspy halo problem, and it centers on a stark disagreement between what our most sophisticated supercomputer simulations predict and what we actually observe when we study the dark matter halos of dwarf galaxies. According to the prevailing cold dark matter model, the relentless pull of gravity should sculpt these halos into a very specific shape. The simulations consistently show a density profile that rises sharply and steeply toward the very center, creating what physicists call a cusp. Imagine a mountain that gets steeper and steeper the closer you get to its peak. The density of dark matter is predicted to behave in a similar way, becoming incredibly dense at the galactic core. This result is not a fluke. It's a robust and repeatable prediction that emerges naturally from the physics of how cold, collisionless particles collapse under their own gravity. Yet, when astronomers turn their telescopes to real dwarf spheroidal galaxies orbiting our Milky Way, they find something quite different. Instead of a sharp, dense cusp, the dark matter distribution in these galaxies appears to be much smoother and flatter in the center, what is termed a core. The evidence for this comes from carefully measuring the velocities of stars within these dwarfs. The speed at which these stars orbit is a direct tracer of the gravitational pull, and thus the mass holding them in place. In galaxy after galaxy, the stellar motions suggest the dark matter density is not peaking dramatically at the center, but is instead distributed in a gentle, almost uniform core. It's the difference between a steep, pointed spire and a softly rounded hill. This discrepancy between the simulated cusps and the observed cores is a serious and persistent problem that has occupied cosmologists for decades. So, what could be causing this fundamental mismatch? Scientists are exploring two broad and fascinating possibilities. The first suggests that our understanding of dark matter itself might need a revision. Perhaps dark matter is not completely cold and inert. What if it possesses some small, intrinsic property that allows it to interact with itself? Not through the electromagnetic force, of course, but through some other, unknown force unique to the dark sector. If dark matter particles could collide or scatter off one another, even very weakly, this self-interaction could effectively smooth out the dense central cusp over billions of years, transferring energy from the outer parts of the halo inward to erase the sharp peak and create a flatter core. This is a compelling idea, but it requires introducing new physics beyond the standard model of particle physics. The second, and perhaps more dramatic, possibility is that the solution lies not with dark matter, but with the ordinary matter that simulators have historically treated as a passive bystander. For a long time, cosmological simulations focused almost exclusively on the gravitational drama of dark matter, treating gas and stars as simple tracers of the underlying mass. But we now know that normal matter can fight back with tremendous force. When the first stars formed in the centers of these early dwarf galaxies, they didn't just shine, they lived violent, short lives and died in colossal supernova explosions. These explosions would have unleashed unimaginable amounts of energy, blasting powerful winds outwards and violently shaking the gravitational foundation of the entire dwarf galaxy. This process, known as gravitational feedback, could be the key. The rhythmic pounding of countless supernovae might have literally pushed the dark matter around, transferring energy from the exploding gas to the invisible halo. Think of it like a spoon stirring a cup of coffee. The swirling motion of the liquid, the normal matter, drags and redistributes the grounds, the dark matter at the bottom, preventing them from clumping too densely in one spot. Through this complex baryonic feedback, the explosive power of the first stars could have dynamically heating up the dark matter, causing it to expand outward and erasing the primordial cusp, leaving behind the smooth core we observe today. Resolving the cuspy halo problem is crucial because it gets to the very nature of the dark matter particle itself. If the solution is found through astrophysical feedback, it would be a stunning demonstration of how the ordinary and dark components of the universe, though seemingly separate, engage in a complex cosmic dance that shapes the structures we see. If, however, the solution requires self-interacting dark matter, it would be a monumental discovery, opening a window into a whole new dark sector of physics with forces and particles we have yet to imagine. The answer likely lies in building ever more detailed simulations that incorporate the full, violent story of star formation and supernova, and in making ever more precise observations of the faintest dwarf galaxies. It's a meticulous process of matching theory to reality, one starlit orbit at a time. But as we map the invisible architecture of dark matter and listen to the echoes of the first stars, our story inevitably turns toward the future. Gazing back at the universe's fiery beginning isn't just about uncovering our origin. It's also about searching for clues to our ultimate destiny. The same primordial conditions that set the stage for galaxies and life might also hold the secret to how the entire cosmic story will end. The properties of dark energy, the very same force accelerating the expansion of the universe today, could have been written into the cosmos's blueprint during those first fleeting instants. To understand where we are going, we may need to look back to where we all began. One of the most discussed and perhaps most peaceful endings is known as the heat death or the Big Freeze. This is the ultimate triumph of entropy, the natural tendency of all systems to move toward disorder. Imagine a universe that continues to expand and accelerate forever, driven by the relentless push of dark energy. Over trillions upon trillions of years, all the usable energy in the cosmos will gradually be exhausted. Stars will burn through their fuel and die. Galaxies will evaporate as their stars drift apart or get flung into the void, and even the black holes will slowly evaporate away through a process known as Hawking radiation. The universe will become a cold, dark, and incredibly dilute soup of fundamental particles and radiation, all at a uniform, frigid temperature mere fractions of a degree above absolute zero. In this state, no more work can be done, no new stars can form, and no complex processes can occur. It is a quiet, eternal, and profoundly lonely conclusion, a universe that has effectively run down like a forgotten clock. The seeds for this ending might be found in the initial, near-perfect smoothness of the early universe, a low-entropy starting point that could only ever evolve toward a higher, more disordered state. A far more dramatic and violent alternative is the Big Rip scenario. This fate hinges on a specific and terrifying property of dark energy. What if its repulsive force doesn't remain constant but actually grows stronger over time? A form of dark energy known as phantom energy could possess this exact property. In this model, the acceleration wouldn't just continue, it would exponentially increase, eventually overcoming all other forces in the universe. First, the expansion would tear apart galaxy clusters, then individual galaxies. As the acceleration ratcheted up, it would rip stars from their galaxies and planets from their stars. In the final moments, about 22 billion years from now in some models, the tearing force would become so powerful that it would overwhelm the forces holding atoms themselves together. Electrons would be ripped from their nuclei, and even protons and neutrons would be shredded into their constituent quarks. The universe would end in a catastrophic, instantaneous flash, with the very fabric of space-time itself torn asunder. The potential for this ending is tied directly to the equation of state of dark energy, a value that could have been determined by quantum fields active during inflation. There are other, more cyclical possibilities. The Big Crunch is a classic idea where the expansion eventually slows, halts, and reverses, pulling all matter and energy back together in a fiery collapse, a mirror image of the Big Bang. While our discovery of accelerating expansion seems to have ruled out a simple crunch, more complex models suggest a rebound. Some theories, like conformal cyclic cosmology, propose that the universe undergoes an endless cycle of expansion and renewal. In this view, the distant heat-death fate of our universe, spread out into a vast, cold emptiness of low-energy photons, somehow becomes mathematically identical to the high-temperature, high-density singularity of a new Big Bang. The end of one cosmos becomes the beginning of the next in an eternal, timeless loop. The initial density and geometry of our universe, set during inflation, would be the crucial factors determining if such a cyclical destiny is even possible. The most profound clue to our fate lies in the nature of the dark energy that is currently dominating the cosmos. Is it truly a constant, immutable force woven into the vacuum of space itself, as Einstein's cosmological constant suggests, or is it a dynamic field known as quintessence that can change in strength over time? The answer to this question, which is one of the biggest in modern cosmology, will almost certainly decide the universe's ultimate destiny, and the key to answering it might be hidden in the universe's first moments. The same quantum fields that drove inflation could have decayed into the dark energy we see today. By studying the precise patterns in the cosmic microwave background, physicists are looking for any tiny, telltale anomalies, a slight preference for certain sizes of fluctuations over others, that could reveal if dark energy was present and active in some form during the universe's infancy and what its fundamental properties are. Ultimately, the story of our universe is a single, continuous narrative stretching from a mysterious beginning to an uncertain end. The initial conditions, the inflationary expansion, the balance of matter and energy, all of these factors set a trajectory that is still playing out some 13.8 billion years later. The quest to understand the early universe is therefore more than historical curiosity. It is an act of cosmic fortune-telling. By deciphering the clues frozen into the oldest light and encoded in the distribution of galaxies, we are not just reading the first chapter of our story. We are trying to skip to the very last page to understand whether the cosmos is destined for a quiet fade, a violent tear, or a magnificent rebirth. Yet for all the clues we've pieced together from the cosmic dawn, one of the most profound and mind-expanding possibilities remains entirely theoretical, an idea that pushes the boundaries of science and philosophy alike. This is the multiverse hypothesis, the startling suggestion that our entire cosmos, with its specific set of physical laws and constants, might be just one bubble in a vast, perhaps infinite cosmic foam. The very conditions that made our universe possible, from the precise strength of gravity to the mass of an electron, might not be a unique, fine-tuned miracle, but simply a lucky roll of the dice in a grand cosmic casino where every possible outcome is played out somewhere. The journey to this radical idea begins not with wild speculation, but with our most successful theory of the early universe, cosmic inflation. Remember that period of hyper-fast expansion. One of the most fascinating consequences of the mathematics behind inflation is that it might be eternal. The theory suggests that the inflaton field, the energy driver of this expansion, may not have decayed everywhere at once. Instead, inflation could have ended only in localized patches, like bubbles spontaneously forming in a pot of boiling water. Within each of these bubbles, the inflaton field drops to a lower energy state, releasing its pent-up energy to create a hot, dense universe like our own, a Big Bang event. But outside of these bubbles, in the wider background, the inflaton field remains high, and inflation continues relentlessly, stretching space at an exponential rate. This means new bubbles are constantly being formed in the ever-expanding inflationary background. Each of these bubbles is a separate, causally disconnected universe, forever out of reach from any other. In this eternal inflation scenario, the multiverse isn't just a possibility. It's an inevitable byproduct of the physics that gave us our own cosmos. This provides a powerful and, to some, comforting answer to the puzzle of fine-tuning. Why do the fundamental constants of nature seem so perfectly set to allow for galaxies, stars, planets, and life? If there is only one universe, this appears to be an unbelievable coincidence. But in a multiverse where every possible value for these constants is realized in some universe, it's no longer surprising. We simply find ourselves in one of the rare universes where the numbers work. It's like winning the lottery. If only one ticket is sold, it's a miracle. If trillions of tickets are sold, a winner is inevitable. We are that winner, living in a universe hospitable to our existence, while an unimaginable number of other universes may be stillborn, collapsing instantly, or expanding too rapidly for atoms to form, or governed by forces too weak to ever create structure. Beyond inflation, other branches of physics point toward the multiverse. String theory, a leading candidate for a theory of quantum gravity, suggests there are perhaps 10 to the 500 possible stable configurations for the extra dimensions it proposes. Each configuration would result in a different set of physical laws and constants. If string theory is correct, then each of these configurations could correspond to a different universe within a vast multiverse, a landscape of possibilities of truly staggering proportions. Even the quantum mechanics of our own universe offers a version known as the many worlds interpretation, where every quantum decision branches reality into a new world. While this is a different type of multiverse, it adds to the overarching theme that our classical intuition of a single, objective reality might be profoundly incomplete. The greatest challenge, of course, is evidence. How can we possibly test for the existence of other universes if they are, by definition, beyond our cosmic horizon? Scientists are exploring ingenious, if speculative, ways to look for clues. One possibility is that our universe might have collided with another bubble universe in the distant past. Such a colossal event could have left an imprint on the cosmic microwave background, a strange, circular pattern of temperature variations that cannot be explained by any standard cosmological process. Astronomers have actively searched for these bruises in the CMB, and while some candidate anomalies have been found, none have been confirmed as definitive proof. Another avenue involves the mysterious dark energy. Its value in our universe seems curiously small. perhaps this value is not fundamental but is instead a random outcome that varies across the multiverse. The distribution of these values could leave a statistical fingerprint on the large-scale structure we observe. If future galaxy surveys were to find that our universe is atypically smooth or structured in a specific way, it could indicate that we are part of a wider multiverse where such conditions are rare. We are essentially trying to discern the shape of the casino by studying our one winning lottery ticket. The multiverse hypothesis forces us to confront the very nature of science itself. Is a theory that predicts an infinite number of unobservable universes still scientific? Proponents argue that it is, if it provides the best explanation for the observable facts of our own universe, namely its puzzling fine-tuning. Critics counter that it risks becoming an unfalsifiable notion, a retreat from explanation rather than an advance. Yet, the history of science is filled with concepts that were once thought untestable, from the existence of atoms to black holes to the Big Bang itself, that were later confirmed. The multiverse may simply be the next great frontier, a paradigm so vast that we are only just beginning to develop the tools, both mathematical and observational, to grapple with its implications. It suggests that the ultimate context for our existence is far grander and stranger than we ever imagined, a humbling reminder that our cosmic home, for all its majesty, might be just one room in an infinite mansion. We've tracked the birth of the first black holes, those primordial giants that could have seeded the entire cosmos. But these ancient objects present us with a puzzle so deep it strikes at the very core of our understanding of reality. This is the black hole information paradox, and it begins with a seemingly simple question with an impossibly complex answer. What happens to the stuff that falls in? When an object crosses a black hole's event horizon, the point of no return, it vanishes from our universe. All that remains, according to Einstein's general relativity, are three simple properties: mass, electric charge, and spin. Everything else about that object, its shape, its chemical composition, the story of its life, the memory of its origin, seems to be utterly erased, scrubbed from existence. This presents a catastrophic problem for physics because quantum mechanics, our other pillar of understanding, has a fundamental, unbreakable rule: information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. This is called unitarity. If you burn a book, the information isn't gone. It's just converted into the specific arrangement of atoms in the smoke and ash. With perfect knowledge, you could theoretically reverse the process and reconstruct the book. A black hole, according to relativity's purest interpretation, doesn't burn the book, it annihilates it from the ledger of the universe entirely. This creates a direct contradiction between our two most successful theories, a paradox that suggests our fundamental view of reality is missing a crucial piece. The plot thickened dramatically in the 1970s when Stephen Hawking made a stunning discovery. He realized that black holes aren't completely black. Due to weird quantum effects happening just outside the event horizon, they slowly leak radiation. This Hawking radiation is incredibly faint, but it carries energy away from the black hole, causing it to gradually lose mass and evaporate over astronomical timescales. Here's the terrifying part. Hawking's calculations showed that this radiation is purely thermal. It's random noise, like the heat coming off a stove element. It contains no information whatsoever about what fell into the black hole. So, if you let a black hole fully evaporate, it would seemingly vanish in a final puff of this random radiation, and all the information about every star, planet, or book that ever fell in would be permanently lost to the universe. This became known as the information paradox. Hawking himself initially believed this meant quantum mechanics had to be modified, that information was truly lost, an idea so unsettling it was famously dubbed by physicist John Preskill as tantamount to burning the textbooks. For decades, this was the unsettling stalemate. Either general relativity was wrong about the nature of the event horizon, or quantum mechanics was wrong about the preservation of information. Most physicists sided with quantum mechanics, trusting that information must be preserved somehow. But how? Where could it possibly be hiding? One early, mind-bending proposal was that the information isn't inside the black hole, but is somehow encoded on its surface, on the event horizon itself. This is the holographic principle, which suggests that all the information about a three-dimensional volume of space can be represented on a two-dimensional boundary that surrounds it, like a cosmic hologram. In this view, when an object falls in, its information isn't lost. It's smeared and stored in Planck-sized pixels on the event horizon, and then slowly radiated back out in the Hawking radiation over eons. The radiation only appears random to a crude observer. If you could collect every single photon of Hawking radiation from the black hole's entire multi-billion-year lifespan, you could, in theory, decode it and reconstruct the entire history of what fell in. A more recent and revolutionary development has come from string theory, offering a potential concrete mechanism for how this information escape might work. The idea involves a concept called complementarity and later firewalls. It suggests that from the perspective of an outside observer, an object never actually crosses the event horizon. Instead, because of time dilation effects, it appears to slow down, get red-shifted into oblivion, and have its information encoded on the surface. However, from the perspective of someone falling in, they would cross the horizon uneventfully. This is a paradox in itself, two contradictory experiences both being true. To resolve this, some theorists propose that the event horizon might not be the quiet place we thought, but a searing wall of high-energy particles, a firewall, that would instantly incinerate any infalling object, preserving its information on the surface but violating the central tenet of relativity that says crossing the horizon should be uneventful. The debate over firewalls shows just how deep the paradox runs, forcing us to choose between cherished principles of our two most fundamental theories. For primordial black holes, this mystery takes on a special significance. These ancient objects, formed in the first second of the universe, would have had ample time to completely evaporate through Hawking radiation. If information is truly lost, then the cosmos is littered with the graves of these black holes, each one a tombstone marking a fundamental violation of the laws of physics. Every one that evaporated would have erased a little bit of the universe's history, leaving our cosmic story permanently incomplete. But if information is preserved, as most physicists now believe, then those same evaporated black holes have performed the ultimate magic trick. They took the information of whatever fell into them in the early universe, perhaps exotic particles, quantum fluctuations, or even whole regions of space-time, scrambled it with impossible complexity, and then faithfully radiated it all back out over billions of years, reintegrating it into the fabric of the cosmos. The answer to this paradox doesn't just lie in the abstract. It is the key to a theory of everything, a framework that must successfully merge gravity and quantum mechanics. Until we solve it, we cannot truly claim to understand how the universe works, from its very first moments to its final fate. But if the mysteries of black holes test the limits of our theories, they are not the only profound puzzle written into the fabric of reality. There is another, more subtle but equally deep problem that has troubled physicists for decades, one that asks why the universe seems to be built on such a wildly uneven playing field. This is known as the hierarchy problem, and it centers on a single, stunning number that seems to defy all natural explanation. Gravity is unimaginably, almost embarrassingly, weaker than all the other fundamental forces. To grasp the sheer scale of this disparity, consider a simple experiment. Take a small, everyday refrigerator magnet. That tiny magnet, using the electromagnetic force, can overcome the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons, and leap up to stick on your fridge. The electromagnetic force is stronger than gravity by a factor of about 10 to the power of 36. That's a 1 followed by 36 zeros. It is a number so vast it transcends human comprehension. You could express it as a trillion times a trillion times a trillion, and you still wouldn't be close. This isn't just a small difference, it's a chasm of cosmic proportions. The strong nuclear force which holds atomic nuclei together is even more powerful. This raises a deeply unsettling question for physicists. Why, in a universe that often values symmetry and elegant equations, why is one of the 4 fundamental forces such a spectacular outlier? The heart of the hierarchy problem lies in the world of quantum field theory and the Higgs boson. The mass of the Higgs, which we've measured at the Large Hadron Collider, is about 125 times the mass of a proton. This seems like a reasonable number until you consider the quantum corrections that should be affecting it. In the quantum world, empty space is not truly empty. It's a seething, temporary foam of virtual particles constantly blinking in and out of existence. These virtual particles should interact with the Higgs field and drive its mass up to the highest energy scales in physics, like the Planck scale where quantum gravity becomes important. This would suggest the Higgs mass should be a whopping 10 to the power of 19 times larger than it actually is. It's as if you dropped a pencil and, against all expectations, it shot through the ceiling, through the atmosphere, and into deep space. The fact that the Higgs mass is relatively light and that the weakness of gravity is therefore preserved seems to require a miraculous, perfect cancellation between these enormous quantum corrections. To a physicist, this kind of fine-tuning feels like a cheat, a sign that our theory is incomplete and that there must be a deeper mechanism at work. One of the most compelling solutions to this puzzle comes from a revolutionary idea about the very shape of reality itself, the existence of extraspatial dimensions. In our everyday experience, we live in 3 dimensions of space and 1 of time. But what if that's not the whole story? Theories like string theory propose that there are actually additional, tiny, curled-up dimensions of space, far too small for us to perceive directly. This isn't just wild speculation, it's a mathematical necessity for making string theory consistent. The hierarchy problem gives these extra dimensions a potential job. Imagine that the fundamental forces of nature are not all living on the same playing field. Perhaps the electromagnetic, strong, and weak forces are confined to our familiar 3-dimensional brain of existence, short for membrane, while gravity is unique. Gravity, described by the geometry of spacetime itself, might be the only force that can freely propagate into these extra dimensions. This changes everything. If gravity is spreading out into these additional dimensions, its strength would be diluted from our 3-dimensional perspective. Think of it like this. If you have a watering can, the water pressure right at the spout is strong and direct. But if that same amount of water had to spread out and water an entire vast field, its intensity at any one point would become very weak. In this scenario, gravity isn't fundamentally weak. It only appears weak to us because we are trapped on our 3-dimensional brain, sensing only a tiny fraction of its full strength leaking into our world. The other forces trapped with us seem strong by comparison. This elegant idea, often called the warped extra dimensions or brain world model, could explain the staggering gap between gravity and the other forces without any need for unnatural fine-tuning. The hierarchy isn't a problem, it's a clue pointing to the larger architecture of the cosmos. Other theoretical frameworks approach the problem from a different angle, proposing new symmetries of nature. Supersymmetry, for instance, is a beloved theory among particle physicists that posits every known particle has a hidden superpartner particle. The beauty of this symmetry is that the quantum contributions from a particle and its superpartner would be equal in magnitude but opposite in sign, perfectly cancelling each other out and protecting the Higgs mass from being driven to impossibly high values. In a supersymmetric universe, the hierarchy problem is solved naturally and elegantly. However, despite decades of searching, we have not yet found any direct evidence for these superpartner particles at the energies we've probed, leaving this beautiful solution in a state of suspense. The hierarchy problem is more than an abstract puzzle for theorists. It is a direct challenge to our understanding of naturalness in the universe. It forces us to ask whether the constants of nature are simply arbitrary, lucky accidents, or if their values are the inevitable outcome of a deeper, more complex reality that we have only begun to glimpse. The staggering weakness of gravity, which allowed for the formation of vast, delicate structures like galaxies and planets instead of a universe that instantly collapsed into black holes, may be the very reason we are here to ponder it. Solving this mystery won't just tidy up our equation. It will almost certainly open a door to a new realm of physics, revealing whether we live in a universe with hidden dimensions, hidden particles, or something even more astonishing that we have not yet dared to imagine. Yet if the staggering weakness of gravity presents one hierarchy problem, the nature of empty space itself presents another, even more baffling discrepancy. This is the vacuum energy problem, and it represents not just a gap in our understanding, but a chasm so wide it has been called the worst theoretical prediction in the history of physics. It all begins with a seemingly simple question: what is the energy of nothing? According to quantum field theory, the vacuum of space is not a true nothingness. It is a seething, frothing sea of activity, where virtual particle-antiparticle pairs constantly blink in and out of existence. These fleeting fluctuations are real. Their effects have been measured in laboratories through phenomena like the Casimir effect, where two metal plates placed incredibly close together in a vacuum feel a slight push because fewer virtual particles can form between them than outside. Every cubic centimeter of empty space, according to our best quantum theories, should be boiling with this fundamental energy. Here is where the problem becomes almost comically large. When physicists attempt to calculate the total energy density of this quantum vacuum, they sum up the contributions from all possible fields and all possible vibrational modes of those fields, all the way up to the highest energy scales they can imagine. The result is a number of such immense proportions it defies any sense of scale: 10 to the power of 112 ergs per cubic centimeter. This is the calculated vacuum energy. Now, let's compare that to the value we actually observe. We can measure the energy of empty space indirectly through its effect on the cosmos. It is, after all, what we call dark energy, the force causing the universe's expansion to accelerate. The observed value for this dark energy density is shockingly small, just 10 to the power of -8 ergs per cubic centimeter. The difference between the colossal theoretical prediction and the tiny observed value is a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. To call this a discrepancy is like comparing the size of a single proton to the size of the entire observable universe and then squaring that ratio. It is by far the largest and most embarrassing mismatch between theory and observation in all of science. If the quantum calculation were even remotely correct, the repulsive force of this incredible vacuum energy would have ripped every atom, every nucleus, and every fundamental particle in the universe apart within a fraction of a second after the Big Bang. The fact that we exist to notice the problem is proof that the calculation is spectacularly wrong, or that something profound is missing from our equations. So where did we go so astray? The core of the issue lies in the way we treat the contributions from these virtual particles. Our current method of summing them up is akin to trying to calculate the exact water level of the ocean by counting every single wave and ripple, including the tiny splashes made by individual raindrops. It's a calculation that is incredibly sensitive to the highest, most extreme energies at the Planck scale, where we know our current theories break down and a theory of quantum gravity must take over. Physicists had hoped that a principle called supersymmetry could come to the rescue. In a perfectly supersymmetric universe, the contributions from particles and their superpartners would be perfectly balanced, with positive and negative values cancelling each other out exactly, leaving a net vacuum energy of zero. That would be a beautiful and natural solution. However, we do not live in a perfectly supersymmetric universe. We've seen no evidence of these superpartners at the energies we can probe. So the cancellation must be imperfect, leaving behind the small but non-zero value we see. But why is the leftover so incredibly minute? The cancellation would have to be precise to 1 part in 10 to the 120, a level of fine-tuning that feels absurd and deeply unsatisfying. This has led to some of the most radical and speculative ideas in modern cosmology. Some theorists propose that the value of the vacuum energy isn't determined by fundamental law, but is instead a random variable that can take on different values in different regions of a vast multiverse. In most of these regions, the vacuum energy is enormous, and the universe either collapses instantly or flies apart too quickly for any structure to form. We, of course, find ourselves in one of the incredibly rare bubbles where the value is minuscule and life can emerge. This anthropic explanation is controversial, as it shifts the question from why this value to we exist, so the value must be right, which some physicists feel is a retreat from a true physical explanation. Other ideas are even more mind-bending, suggesting that the vacuum energy might not be a true constant, but something that has dynamically relaxed to zero over time through some unknown mechanism. Or perhaps gravity behaves differently when responding to the energy of the vacuum than it does to the energy of normal matter, a modification that could sever the link between the quantum calculation and the gravitational effect. The vacuum energy problem is more than a mathematical annoyance. It is a direct confrontation with the limits of our knowledge. It screams that our two greatest theories, quantum mechanics and general relativity, are fundamentally incompatible when pushed to their extremes, and that unifying them will require a revolution in physics as profound as those ushered in by Einstein and Planck. The incredible emptiness of space may hold the key to the next great leap in our understanding of reality. Imagine if the answer to one of our greatest cosmic mysteries, the nature of dark matter, was hiding in plain sight, not as an exotic new particle, but as countless ancient gravitational traps forged in the universe's first second. This is the compelling premise behind the idea of primordial black holes. What if the dark matter holding galaxies together isn't a sea of invisible particles, but a vast swarm of black holes that formed not from dying stars, but directly from the extreme densities of the Big Bang itself? The appeal is undeniable. It's an elegant, almost minimalist solution that uses known physics, gravity, to explain the unknown without needing to invent new particles or forces. To form a primordial black hole, you need a region of space in the very early universe that's just a little denser than its surroundings. In the chaotic maelstrom of the first instance, quantum fluctuations from inflation could have created such overdense patches. If one of these patches collapsed under its own weight before expanding away, it could have crossed its own Schwarzschild radius and pinched off into a black hole. The mass of that black hole would be tied directly to the time it formed. One born when the universe was a mere second old could be as massive as 1,000 suns, while one formed a fraction of a second later might be no heavier than an asteroid. This means a universe filled with primordial black holes wouldn't be a monochromatic crowd. It would be a diverse population of dark objects spanning an incredible range of masses. For a time, this was a perfectly viable and exciting candidate for dark matter. A sufficient number of these primordial black holes, drifting unseen through galactic halos, could provide all the gravitational glue needed to explain the rotation curves of galaxies and the bending of light from distant quasars. But science advances by putting ideas to the test, and over the past few decades, astronomers have devised incredibly clever ways to search for these dark relics. The primary method is through their gravitational influence on the light of background stars, an effect called microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act like a lens, briefly magnifying the star's light in a predictable way. By monitoring millions of stars for these telltale flashes, we can census the population of invisible compact objects in our galactic halo. The results from these meticulous surveys have been increasingly restrictive. For black holes in a wide range of masses, particularly those around the mass of our Sun, the microlensing data shows they are far too scarce to account for more than a tiny fraction of the dark matter. Other constraints come from watching the precise timing of millisecond pulsars. A black hole passing between us and the pulsar would subtly delay its ticks, and the absence of such delays rules out large numbers of certain mass ranges. Even the incredible precision of the LIGO and Virgo gravitational wave observatories has weighed in. The black hole mergers they've detected are fascinating, and some could indeed be primordial, but their estimated numbers are again far too low to explain the dark matter. So has the case been closed? Not entirely. There remains a few intriguing narrow windows. One is for very low-mass black holes, sometimes called asteroid-mass black holes. These would have evaporated by now due to Hawking radiation if they were too small, but there's a sweet spot where they could still exist and are difficult to detect with current microlensing surveys. Another window is open for truly colossal primordial black holes, those with masses tens of times that of our Sun or greater. While they couldn't be numerous enough to be all the dark matter, they could still make up a portion of it. The gravitational wave signals from merging black holes have opened our eyes to a population of black holes whose masses are larger than we expected from stellar collapse, leaving the door open for a primordial origin for at least some of them. Even if they aren't the dominant dark matter, primordial black holes could still have played a starring role in cosmic evolution. They might have been the seeds for the supermassive black holes that now reside at the centers of galaxies, providing a massive head start that solves the timing problem of how they grew so big so quickly. They could have catalyzed the formation of the very first stars and galaxies, their immense gravity acting as nucleation points for collapsing gas in the early universe. The hunt for them continues, not just as a dark matter candidate, but as potential fossils from the cosmos's explosive beginning. Their confirmed discovery would be a direct window into the conditions of the Big Bang, proving that the universe's earliest moments were wild enough to knot spacetime itself into permanent dark knots. Their elusive nature reminds us that the dark universe still holds secrets, and that the answers to our biggest questions may be written in the gravity of the oldest objects in existence. And so we arrive at the final and perhaps most personal mystery on our journey, the breathtaking specificity of the universe's initial conditions. After exploring 29 profound puzzles from the singularity to the great silence, we are left staring at a cosmic balance sheet of astonishing precision. The fundamental constants of nature, the strength of gravity, the mass of an electron, the precise energy levels in a carbon atom, all seem perfectly dialed in to allow for a cosmos that is not just stable but creative. A universe that doesn't just exist, but that blossoms with galaxies, stars, planets, and beings capable of wondering how it all came to be. This isn't just a single lucky break. It's a chain of coincidences so long and so improbable it defies belief. The force of gravity, for instance, is exquisitely tuned. If it were even slightly stronger, the universe would have collapsed back on itself in a fiery big crunch eons ago. If it were slightly weaker, matter would have flown apart too rapidly to ever coalesce into the first stars. The expansion rate set by the Big Bang was also Goldilocks perfect. If it had been 1 part in a million faster, the universe would be a cold, empty void. 1 part in a million slower, and it would have recollapsed almost immediately. The list goes on and on, from the precise nuclear resonances that allow for the formation of carbon in stellar furnaces to the incredible weakness of gravity that allows for the formation of vast, delicate structures instead of a universe composed solely of black holes. This staggering fine-tuning presents us with a question that straddles the line between science and philosophy. Are we the beneficiaries of incomprehensible cosmic luck, or is there a deeper principle at work? One compelling answer emerges from the multiverse hypothesis we just explored. In this view, our universe is not unique. It is one bubble in a vast, perhaps infinite cosmic foam. In this grand multiverse, every possible set of physical laws and constants is realized somewhere. Most of these universes would be stillborn, collapsing instantly, or expanding too fast for atoms to form, or governed by forces too weak to ever create a single molecule. In such a reality, it is no surprise that we find ourselves in one of the rare, hospitable universes. We are the inevitable product of a cosmic selection bias. We can only observe a universe capable of producing observers. This anthropic reasoning provides a naturalistic explanation for the fine-tuning, but to some, it can feel like a retreat from a more fundamental physical explanation, a way of saying the answer is beyond our ability to ever observe directly. Another possibility is that the fine-tuning is not an accident at all, but a clue pointing toward a deeper, unified theory of physics that we have not yet discovered. Perhaps the constants we perceive as free parameters are not arbitrary. Maybe they are the inevitable outcome of a single, overarching physical principle, much like the way the value of pi is not arbitrary but is fixed by the geometry of a circle. In this view, the apparent fine-tuning is an illusion created by our incomplete knowledge. Once we have a true theory of everything, perhaps one that successfully merges quantum mechanics and gravity, these constants will be revealed as the only possible values that allow for a logically consistent cosmos. The challenge, of course, is that such a theory remains elusive, the holy grail of modern physics. There is a third, more radical perspective, that the universe is in some sense participatory, that the act of observation itself is intertwined with its existence. Some interpretations of quantum mechanics have long suggested that the observer plays a role in determining reality. Could it be that the universe is structured to give rise to consciousness because consciousness is a fundamental part of the process that brings it into being? This is a highly speculative and controversial idea, but it speaks to the deep mystery of why a universe that began in a state of near-featureless energy should, 13.8 billion years later, become aware of itself. Ultimately, the mystery of the initial conditions is the mystery of our own existence. The same physical laws that govern the spin of a galaxy also govern the chemistry of our brains. The carbon in our cells was forged in the hearts of long-dead stars. We are not just inhabitants of the universe, we are a product of it, a way for the cosmos to know itself. The fact that the universe has both an origin and a set of laws that allow for that origin to be investigated may be the most profound discovery of all. It suggests that whether through luck, necessity, or something beyond our current understanding, the universe is fundamentally intelligible. Our relentless drive to understand the cosmos, to ask these 30 great questions, might not be an accidental byproduct of evolution, but a reflection of a deeper cosmic purpose we are only just beginning to glimpse. The story is not finished. The final chapter has yet to be written, and we are both its authors and its characters. And so as we stand here at the end of our journey, looking back across the breathtaking expanse of cosmic history we've explored, it's clear that our greatest discovery is not any single answer, but the overwhelming depth of our own curiosity. These 30 mysteries are not a checklist of problems to be solved and filed away. They are a living, breathing testament to the universe's profound complexity. We've ventured from the inexplicable singularity at the precipice of time itself, through the inflationary burst that set the cosmic stage, and into the long, patient darkness where the first starlight fought to ignite. We've grappled with the ghostly presence of dark matter shaping the cosmos and the repulsive push of dark energy dictating its fate, all while trying to understand why we are even here to witness it, surrounded by a great and puzzling silence. This exploration reveals a beautiful and humbling truth that the universe is not a puzzle to be completed, but an endless frontier of wonder. Each time we pull back one curtain of mystery, we find another, even more intricate and fascinating, waiting behind it. The horizon of our knowledge constantly expands, but so too does the shoreline of the unknown. The initial conditions of the Big Bang, the quantum fluctuations frozen into the first light, the violent birth of the first black holes, these are not just historical footnotes. They are the foundational chapters of our own story, written into the very atoms that make up our bodies and the planets we call home. We are the universe's way of beginning to understand itself, a product of its laws, gazing back in awe at its own origins. This endless quest, this drive to ask how and why, is perhaps the most human thing about us. It connects the first person who looked up at the starry sky in wonder to the teams of scientists analyzing data from our most powerful telescopes today. The journey through these mysteries doesn't provide finality, it provides context. It situates our brief, brilliant lives within an epic narrative spanning billions of years, giving us a role to play as the conscious agents of a cosmos seeking to know its own nature. The work is far from over. The next great discovery is waiting, hidden in the data of a new telescope, in the equations on a theorist's chalkboard, or in the mind of a young person just now looking up at the night sky for the very first time, their imagination set ablaze by the same timeless questions that have captivated us for millennia. But the greatest discoveries are never truly behind us. They are always on the horizon, waiting for the next tool, the next idea, the next generation of explorers to bring them into focus. And right now, we are in the midst of a golden age of cosmic discovery, armed with an arsenal of next-generation observatories that are poised to crack the very mysteries we've been exploring. We are no longer just passive observers of the cosmos. We are active detectives, building the instruments that will finally allow us to read the universe's earliest diary entries. Leading this charge is the James Webb Space Telescope, an infrared marvel that is already rewriting the textbooks. Its profound infrared sensitivity is like a time machine, allowing it to peer back further than any telescope before it, to an era when the very first galaxies were just beginning to coalesce out of the primordial darkness. Webb isn't just looking for these infant galaxies, it's studying their chemistry. By analyzing the light from these incredibly distant objects, its spectrographs can detect the faint fingerprints of elements within them. Finding a galaxy that is completely devoid of heavy metals would be the smoking gun for a system lit solely by that first generation of massive, pure hydrogen population 3 stars, finally confirming their existence. Furthermore, by charting the precise growth and evolution of galaxies in the first few 100 million years, Webb is testing our theories of structure formation to their limits, potentially revealing if dark matter is truly cold, or if something more exotic is at work in the cosmic dawn. While Webb studies the light from the first stars, a new window onto the universe is being pried open here on Earth and in space. Gravitational wave observatories are evolving from proving a theory to becoming standard tools for astronomy. The current ground-based detectors like LIGO and Virgo have given us our first glimpses of colliding black holes and neutron stars, but the future lies with even more ambitious projects. The Laser Interferometer Space Antenna, or LISA, is a planned space-based observatory that will detect gravitational waves at a much lower frequency. This will allow it to sense the mergers of the universe's very first supermassive black holes. Hearing these events would be transformative. The frequency and mass of these primordial collisions could tell us if these giants were born from the first stars or from direct collapse, solving a key timing problem that has puzzled us for decades. We will move from simply knowing these events happened to understanding their detailed history, and we cannot forget the hunt for the most elusive particles in the universe. Deep underground, in abandoned mines and tunnels shielded from cosmic rays, incredibly sensitive experiments continue their quiet search for dark matter. While the classic WIMP hypothesis has yet to yield a definitive signal, these null results are themselves guiding us, pushing physicists to consider a wider zoo of possibilities, from ultra-light actions to other exotic weakly interacting particles. The next generation of these detectors, with volumes of liquid xenon or argon scaled up to unprecedented sizes, will be so sensitive that they will either finally detect a dark matter particle or force us to radically rethink one of the cornerstone ideas of modern cosmology. Perhaps the most profound answers will come from the combination of all these tools, giving us a multi-messenger view of the cosmos's birth. Imagine correlating the gravitational wave signal from a pair of merging primordial black holes detected by LISA with a specific metal-poor galaxy observed by Webb. Or imagine a new particle detector finally identifying dark matter, allowing us to then search for its specific annihilation signature in the data from gamma-ray telescopes. This synergistic approach transforms our understanding from a series of isolated facts into a coherent, interconnected story. The next 2 decades promise not just incremental progress, but a potential revolution. We are building the instruments that can test our most daring ideas about inflation, dark energy, and the nature of spacetime itself. The mysteries of the early universe have endured for centuries, but for the first time in human history, we can see the path forward, a trail of technological and intellectual breadcrumbs that leads us toward answers we have only just begun to